Try to picture nothing. Not darkness, because darkness is something. Not silence, because silence is the absence of sound, and absence requires a framework in which things could exist but happen not to. Not emptiness, because even an empty room has walls, has dimensions, has the quiet promise of space waiting to be filled. What you are trying to imagine is a state so thoroughly void that the word void oversells it. No space, no time, no up, no down, no hot, no cold, no here, no there, not even the passage of one moment to the next, because moments do not yet exist, and there is no clock, no pulse, and no rhythm to measure them by. You are trying to imagine the total absence of reality, and the honest truth is that your mind cannot do it. The human brain evolved to track predators across savannas and remember which berries were poisonous. It was never built to contemplate its own non-existence, let alone the non-existence of existence itself. And yet, roughly 13.8 billion years ago, this was all there was. Or rather, this was all there wasn't. And then, without warning, without cause, without a stage on which to perform or an audience to witness it, everything happened. The event that physicists politely call the Big Bang was not, despite what the name suggests, an explosion. Explosions require space to expand into. They require matter to be flung outward. They require a before and an after, a center and an edge, a cause and an effect. The Big Bang had none of these things. It was not a bomb going off in an empty warehouse. It was the warehouse, the bomb, the air, the fire, the shockwave, the sound, and the silence before and after, all appearing simultaneously from nothing, for no reason anyone has ever been able to determine. Space did not exist, and then it did. Time did not pass, and then it began. The laws of physics, which govern every interaction between every particle in every corner of the cosmos, did not apply. And then, suddenly, they did, as though someone had written the rules of a game and started playing it in the same instant with no one to write them and no one to play. This is where the mind begins to buckle, because the question that follows is the most natural question any thinking creature could ask. And it is also the one question that physics cannot answer. What came before? The uncomfortable truth is that before is a word that relies on time, and time is one of the things that was born in that first instant. Asking what came before the Big Bang is like asking what is north of the North Pole. The question is grammatically correct and logically meaningless. Time did not stretch backward from that moment into some infinite hallway of pre-existence. It simply started. The clock began at 0, and there was no negative one. For a species that experiences every waking second as a river flowing from past to future, this is an almost unbearable concept. We want a cause. We want a reason. We want a hand on a lever, a finger on a trigger, a voice in the darkness saying, "Let there be." Physics offers us nothing of the kind. It offers us a singularity, a point of infinite density and infinite temperature and 0 volume, which is really just a sophisticated way of saying that the mathematics breaks down and nobody knows what was actually happening. What physicists can describe with an almost perverse level of precision is what happened after. Not minutes after, not seconds after, but fractions of seconds so small that writing them out requires scientific notation, because the English language runs out of words long before the numbers run out of zeros. In the first sliver of time, a period so brief that calling it an instant is generous, the universe was smaller than an atom and hotter than anything that has existed since. The 4 fundamental forces that govern all of reality, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force were unified into a single superforce, a kind of undifferentiated cosmic energy that contained within it the potential for everything that would ever exist. Stars, planets, oceans, bacteria, the rings of Saturn, the neurons firing in your brain as you read this sentence, all of it was encoded in that first blinding moment, compressed into a space you could not see with the most powerful microscope ever built. Then, in a period known as the Planck epoch, lasting from 0 to roughly 10 to the power of negative 43 seconds after the beginning, something extraordinary and deeply unsettling occurred. Or rather, nothing describable occurred, because this is the period about which physics has almost nothing to say. The Planck epoch is the moment when the universe was so small, so hot, and so dense that the known laws of physics simply do not apply. General relativity, which describes gravity and the behavior of space-time on large scales, collapses. Quantum mechanics, which describes the behavior of particles on the smallest scales, collapses. The two frameworks, which together explain virtually everything humans have ever observed in the natural world, are not just insufficient here, they are incompatible. They give contradictory answers. They break. And so, the first tick of the cosmic clock remains, to this day, a locked room, its contents unknown, its key unfound. Physicists have theories, they have speculations, they have elegant mathematics scrawled on whiteboards in offices at Cambridge and Princeton and Caltech. What they do not have is certainty, and what they may never have is proof. What emerged from the Planck epoch was a universe undergoing the most violent transformation imaginable. Gravity peeled away from the other forces, becoming its own entity, the weakest of the four and yet the one that would ultimately shape the largest structures in the cosmos. The universe was still unthinkably hot, still unthinkably small, but it was beginning to differentiate, beginning to acquire the distinct characteristics that would define it for the next 13.8 billion years. And then, at roughly 10 to the power of negative 36 seconds, something happened that would determine the fate of every atom, every galaxy, every living thing that would ever exist. Inflation. The word is borrowed from economics, which is fitting in a grim sort of way, because what it describes is an expansion so catastrophically rapid that it makes every other event in the history of the universe look sluggish by comparison. In a fraction of a second, a span of time so short that no human analogy can capture it, the universe expanded by a factor of at least 10 to the power of 26. That is not a typo. The observable universe went from something smaller than a proton to something roughly the size of a grapefruit, and it did so faster than the speed of light. This does not violate Einstein's famous speed limit, because that limit applies to objects moving through space, and what was happening during inflation was space itself stretching. The fabric of reality was pulling apart like taffy in the hands of a giant, and everything embedded in that fabric, every quantum fluctuation, every ripple of energy, was being carried along for the ride. The implications of inflation are staggering and, for anyone paying close attention, quietly terrifying. Those tiny quantum fluctuations, random variations in energy density that existed in the pre-inflationary universe, were stretched to cosmic scales. They became the seeds of all structure. Every galaxy, every cluster of galaxies, every vast cosmic web of matter stretching across billions of light years, all of it traces its lineage back to random quantum noise in the first trillionth of a trillionth of a trillionth of a second. The universe is not arranged according to a plan. It is arranged according to dice rolls that took place before atoms existed, frozen in place and magnified beyond comprehension. When inflation ended, and physicists are not entirely certain why it ended, the energy that had driven the expansion was released in a cataclysm of heat. The universe was suddenly flooded with particles, a seething, roiling plasma of quarks and gluons and electrons and photons and neutrinos, all colliding and annihilating and reforming at temperatures exceeding 10,000 trillion degrees. This was the quark-gluon plasma, a state of matter so extreme that it has only been recreated in one place on Earth, inside the Large Hadron Collider at CERN in Geneva, where physicists smash heavy ions together at nearly the speed of light and, for the briefest of instants, produce conditions that last existed a microsecond after the birth of everything. The scientists who run these experiments sometimes joke that they are recreating the beginning of the universe in a tunnel beneath the Swiss countryside. The joke is accurate, and it is not entirely funny. Within that first second, a drama played out that determined whether the universe would contain any matter at all. For every particle of matter created in the furnace of the early universe, a corresponding particle of antimatter was also created. Matter and antimatter are perfect mirror images of each other, identical in every respect except for their charge. And when they meet, they annihilate each other completely, converting their combined mass into pure energy, according to Einstein's equation, relating energy to mass times the speed of light squared. In a perfectly symmetrical universe, every particle would have found its antiparticle, every marriage would have ended in mutual destruction, and the cosmos would have been left with nothing but a cooling bath of radiation. No stars, no planets, no chemistry, no life, no one to wonder why. But the universe is not perfectly symmetrical, and this is perhaps the most consequential mystery in all of physics. For every billion pairs of matter and antimatter particles that annihilated each other in that first second, there was one extra particle of matter left over. One in a billion. A rounding error so small that, in any other context, it would be beneath notice. And yet that tiny asymmetry, that almost negligible imbalance, is the reason anything exists at all. Every atom in your body, every star in the sky, every grain of sand on every beach on Earth, all of it is the leftover residue of a cosmic massacre in which nearly everything was destroyed. You are made of survivors, and they survived not through strength or cunning, but through a statistical fluke so improbable that physicists have spent decades trying to explain it and have not yet succeeded. By the time the universe was 1 second old, and it is worth pausing to appreciate that everything described so far happened within a single second, the temperature had dropped to roughly 10 billion degrees. Protons and neutrons had formed from quarks, bound together by the strong nuclear force. Electrons buzzed through the plasma like gnats in a furnace. Neutrinos, those ghostly particles that barely interact with anything, had already decoupled from the rest of matter, streaming off into space in every direction, and they are still out there, still traveling, a relic of the first second that passes through your body at a rate of about 100 trillion per second, without your ever knowing or caring. In the minutes that followed, the universe became a nuclear reactor. Protons and neutrons began to fuse, forming the nuclei of the lightest elements, hydrogen, helium, and trace amounts of lithium and beryllium. This process, called Big Bang nucleosynthesis, lasted roughly 20 minutes, and when it was over, the elemental composition of the universe was more or less set about 75% hydrogen, about 25% helium, a pinch of everything else. That ratio persists to this day, billions of years later. And it is one of the most powerful pieces of evidence that the Big Bang actually happened, because the predictions made by the theory match the observations made by telescopes with an accuracy that borders on the eerie. But the universe born from this process was not the universe you would recognize. It was opaque. For the next 380,000 years, give or take, the cosmos was a blinding fog of plasma, so hot and so dense that photons could not travel more than a short distance before being absorbed and re-emitted by the surrounding electrons. Light existed in unimaginable quantities, but it could not go anywhere. The universe was bright but unseeable, like being trapped inside the surface of a star. Nothing could form. No structures, no patterns, no complexity. Just a slowly cooling ocean of plasma, expanding and thinning, waiting for a moment that would not come for hundreds of thousands of years. And here is the detail that should unsettle you if you have been paying attention. Everything that would ever happen in the history of the universe, every galaxy that would form, every star that would burn, every planet that would cool, every ocean that would fill, every cell that would divide, every thought that would be thought, was already determined. Not in a mystical sense, not in the sense of fate or destiny, but in the cold, mechanical sense of initial conditions. The quantum fluctuations had been set. The matter-antimatter asymmetry had played out. The ratio of hydrogen to helium had been fixed. The expansion rate had been established. All the information needed to build a universe of 100 billion galaxies, each containing 100 billion stars, was already present, encoded in the temperature variations of a plasma that would not become transparent for another 400 millennia. The universe was a loaded gun, and it had already been fired. Everything after was just the bullet traveling. The question that settles over you, quietly, persistently, like dust on a windowsill, is why. Not why in the sense of purpose, because purpose implies intention, and intention implies a mind, and physics does not deal in minds. But why in the sense of mechanism? Why these laws and not others? Why these constants and not different ones? Why did the matter-antimatter asymmetry fall the way it did? Why did inflation start, and why did it stop? Why is there something rather than nothing? These are not rhetorical questions. They are not philosophical exercises for undergraduates to debate over coffee. They are open, unsolved problems at the frontier of human knowledge. And the honest answer to every single one of them is the same. Nobody knows. The universe emerged from conditions that our best theories cannot describe, governed by principles we have not yet discovered, for reasons that may not exist. And the most terrifying possibility of all, the one that keeps certain cosmologists awake at 3 a.m. staring at their ceilings, is that the answers are not merely unknown, but unknowable. That the first instant of creation is permanently sealed behind a wall of broken physics, and that no amount of cleverness, no particle accelerator, no mathematical framework will ever allow us to see behind it. That we are, and will always be, creatures born inside a story that started before we arrived, reading a book whose first page has been torn out. The universe does not owe us an explanation. It never has. And yet, here it is, 13.8 billion years later, vast beyond comprehension and still expanding, still cooling, still carrying within it the faint echo of that first impossible moment. The cosmic microwave background radiation, a uniform glow of microwave light that permeates all of space, is the afterimage of the moment the universe first became transparent. The moment photons were finally free to travel without being scattered. It is the oldest light in existence. When astronomers point their instruments at it, they are looking at the surface of the last scattering, a wall of light beyond which nothing can be seen, not because nothing is there, but because the universe before that moment was opaque. It is, in a very real sense, the edge of the observable past, and behind it lies a silence that has lasted since the beginning of time. That silence is where the story starts. And the story, as you will come to see, does not get more comforting from here. Consider the sun. You have looked at it, or rather, you have glanced at it and looked away, because staring is not something your eyes will tolerate. It hangs in the sky like a coin held at arm's length, modest, familiar, almost friendly. It rises, it sets, it warms the side of your face through a car window. You do not think of it as extraordinary. You do not lie awake at night marveling at it. And in a sense, you are right not to, because by the standards of the galaxy it inhabits, the sun is an utterly unremarkable star, a middle-aged yellow dwarf, average in size, average in brightness, average in temperature, fusing hydrogen into helium at a perfectly ordinary rate and doing nothing whatsoever to distinguish itself from the roughly 200 billion other stars in the Milky Way. If the galaxy were a city, the sun would not be the mayor or the banker or even the town drunk. It would be a man in a gray coat standing at a bus stop, noticed by no one, missed by no one, doing exactly what every other man in a gray coat at every other bus stop in the city was doing. And yet this unremarkable star is the single most important object in the lives of every organism that has ever lived on Earth. It is the engine of all photosynthesis, the driver of all weather, and the source of nearly all energy that human civilization has ever consumed. From the sunlight stored in ancient forests and compressed into coal over 300 million years, to the photons striking a solar panel on a rooftop in Arizona this afternoon. Without it, the Earth would be a frozen rock, drifting in the dark, its oceans solid ice, its atmosphere collapsed into a thin crust of frozen nitrogen, its surface temperature somewhere around 230 degrees below zero. Everything you have ever known, every person you have ever loved, every meal you have ever eaten, every song you have ever heard, exists because of a medium-sized ball of burning gas, roughly 150 million kilometers away, that happens by pure accident of orbital mechanics, to be exactly the right distance to keep water liquid on the surface of one particular rock. That distance, 150 million kilometers, is what astronomers call one astronomical unit, and it is the first rung on a ladder of measurement that climbs so high that the top is invisible. 150 million kilometers sounds enormous, and in the context of daily life it is. If you drove a car at motorway speed without stopping, the trip would take roughly 170 years. If you walked, assuming you did not need to eat or sleep or age, it would take about 3,400 years. The distance is, by any human measure, absurd. And it is also, by any cosmic measure, trivially small. The Sun's nearest stellar neighbor, Proxima Centauri, sits roughly 4.24 light-years away, which translates to approximately 40 trillion kilometers. Writing that number out in full would fill a line, and comprehending it would fill a lifetime. The fastest spacecraft humanity has ever launched, the Parker Solar Probe, travels at about 690,000 kilometers per hour, and at that speed, it would take roughly 6,500 years to reach Proxima Centauri, to reach the star next door, the one astronomers describe as close. A light year, the unit that makes these distances barely manageable, is itself a monument to absurdity. It is the distance that light, moving at roughly 300,000 kilometers per second, covers in 1 year. That works out to about 9.5 trillion kilometers. Light is the fastest thing in the universe. Nothing with mass can match it, let alone exceed it. And yet when you look up at Proxima Centauri on a clear night, you are not seeing the star as it is now. You are seeing the star as it was 4 years and 3 months ago. The light entering your eye left that star's surface before you had the thought to look up. If Proxima Centauri had exploded this morning, you would not know for more than 4 years. You would stand in your garden tonight, looking at a star that no longer exists, and you would call it beautiful, and you would be wrong, and you would have no way of knowing. This is the first of the quiet horrors embedded in the nature of light travel time. You have never seen the present, not once, not ever. Everything you have ever observed, from the most distant galaxy to the face of the person sitting across the table from you, arrived as light that took time to travel, which means you experienced it after the fact. The delay is negligible at human scales, of course. The light from a face 2 meters away takes about 6 nanoseconds to reach you, a lag so small it is meaningless. But at cosmic scales, the delay becomes monstrous. The light from the Andromeda Galaxy, the nearest large galaxy to the Milky Way, takes 2.5 million years to arrive. You are seeing Andromeda as it was when the genus Homo was just beginning to emerge on the plains of East Africa. The galaxy you observe in your telescope is a ghost. The real Andromeda, the one that exists at this moment, is invisible to you, and will remain invisible to you for another 2.5 million years, by which time you and everyone you know, and every civilization your species has ever built, will have been dust for epochs. Extend this principle outward, and the implications become genuinely dizzying. The observable universe, the sphere of space from which light has had time to reach us since the beginning, spans roughly 93 billion light-years in diameter. That number seems impossible, given that the cosmos is only 13.8 billion years old. But it is explained by the expansion of space itself. The light set out billions of years ago, and the space between its source and us has been stretching ever since. So the objects that emitted that light are now far more distant than the travel time of the photons would suggest. The edge of the observable universe is not a wall. It is not a barrier. It is simply the point beyond which light has not yet had time to reach us. Beyond it, the universe almost certainly continues, possibly infinitely, but we cannot see it, cannot measure it, cannot prove it exists, and may never be able to. We are inside a bubble of visibility, and the bubble has an edge, and beyond the edge there may be more universe than we could explore in 1 trillion lifetimes, or there may be something else entirely, or there may be nothing. And the point is that we do not know, and the universe is not in any particular hurry to tell us. Within that observable bubble, the numbers are already more than the human mind can honestly process. The Milky Way alone contains somewhere between 200 billion and 400 billion stars. That range is itself a quiet confession. We cannot count the stars in our own galaxy to within a factor of 2. We live inside it, and we are guessing. And the Milky Way is one galaxy among an estimated 2 trillion in the observable universe. 2 trillion galaxies, each containing hundreds of billions of stars scattered across a volume of space so large that light itself, the fastest thing in existence, takes 93 billion years to cross it. These are not numbers that the brain was designed to handle. They are not numbers that can be visualized or compared to anything in human experience. They are numbers that exist on paper and nowhere else, because the reality they describe is too vast for any creature that measures its life in decades to absorb. In 1995, a man named Robert Williams decided to do something that many of his colleagues thought was foolish, possibly even career-ending. Williams was the director of the Space Telescope Science Institute, which meant he had a certain amount of discretionary time on the Hubble Space Telescope, and he decided to point it at nothing. Not at a known galaxy, not at a star cluster, not at a nebula or a quasar, or any of the dramatic objects that competed for Hubble's limited observation time. He pointed it at a tiny, apparently empty patch of sky near the constellation Ursa Major, a region so small that you could cover it with a grain of sand held at arm's length. And he left it there, gathering light, for 10 consecutive days. The image that came back changed the way human beings understand the universe. The Hubble Deep Field, as it came to be known, revealed roughly 3,000 galaxies in that single minuscule patch of sky. 3,000 galaxies where there had appeared to be nothing. Not stars within our own galaxy, but entire galaxies, each one a vast island of hundreds of billions of suns, some of them so distant that their light had been traveling for more than 12 billion years. The image was, in a very real sense, a core sample drilled through time itself. In the foreground were bright, well-defined spiral galaxies, relatively nearby, their light only a few billion years old. Behind them, smaller and redder, were galaxies from the Middle Ages of the cosmos, their light stretched by the expansion of space into longer, ruddier wavelengths. And at the very limit of detection, smudges of light so faint that they barely registered on the sensors, were galaxies from the deep past, emitting their light when the universe was still young, still assembling itself from the raw material of the first few 100 million years. If you took that tiny patch and multiplied it across the entire sky, the implication was staggering. The observable universe contains not millions, not billions, but roughly 2 trillion galaxies. And that was just what Hubble could see with the technology of the 1990s. Subsequent surveys, including the Hubble Ultra Deep Field in 2004, which stared at an even smaller patch for a total exposure of roughly 11.5 days, pushed the count further, finding galaxies so distant that their light had been traveling for over 13 billion years, meaning they were seen as they existed less than 1 billion years after the beginning of everything. The James Webb Space Telescope, launched in 2021, has since pushed even deeper. Observing galaxies that formed so early, they challenge existing models of how quickly cosmic structure could have assembled. Every time we build a better camera and point it at the darkness, we find that the darkness is full. And here is the fact that Robert Williams's image revealed most powerfully. The fact that should settle over you like cold water. The universe does not care that you are in it. Every one of those 3,000 galaxies in the Hubble Deep Field contains worlds of its own, stars with planets, planets with moons, systems with chemistry, and possibly, probably, life. And none of them know that Earth exists. None of them have ever received a signal from Earth, because the nearest of them is too far away for any signal humanity has ever sent to have arrived. The radio waves from the first human broadcast, leaking off the surface of the Earth at the speed of light, have been traveling for roughly a century, which means they have covered about 100 light years, which means they have reached an almost embarrassingly small bubble of space containing perhaps a few thousand stars in a galaxy of hundreds of billions, in a universe of 2 trillion galaxies. The cosmic footprint of human civilization, the total volume of space that even knows we are here, is so small in proportion to the whole that expressing it as a percentage requires more decimal places than most calculators can display. In 1990, the Voyager 1 spacecraft, then about 6 billion kilometers from Earth, was instructed to turn its camera around and take a final photograph of home. The resulting image, championed by the astronomer Carl Sagan, showed Earth as a tiny speck, a fraction of a pixel, suspended in a beam of scattered sunlight. Sagan called it the pale blue dot, and what he said about it has been quoted so often that the words have acquired the comfortable weight of familiarity, which is a shame, because what the image actually shows is not comforting at all. It shows that everything that has ever happened in the history of human civilization, every war, every love affair, every symphony, every genocide, every act of kindness, every act of cruelty, every birth and every death, took place on a mote of dust caught in a sunbeam. Not metaphorically, literally. That is what Earth looks like from 6 billion kilometers away, which is still inside our own solar system, which is one system among billions in one galaxy among trillions. The loneliness of this position is not poetic. it is structural. The distances between objects in space are not merely large, they are hostile. The void between stars is not empty the way an unused room is empty. It is empty the way the concept of absence is empty. In every cubic centimeter of interstellar space, you would find, on average, about one atom. One, in a volume that could comfortably fit a sugar cube. The space between galaxies is even more desolate. The intergalactic medium contains roughly one atom per cubic meter, a vacuum so severe that no laboratory on Earth has ever come close to replicating it. If you were placed in intergalactic space, you would not freeze immediately, because there is almost nothing around you to conduct your heat away. You would radiate your warmth slowly into the void, cooling over hours while floating in a darkness so absolute that the nearest visible light, the nearest star, the nearest anything, would be millions of light years away. You would die eventually, but the void would not notice. The void has never noticed anything. It is not capable of noticing. It simply is, vast and patient and indifferent, and it makes up almost all of what exists. This is the scale of the arena in which Earth finds itself, and it is worth dwelling on because human beings have a persistent, almost compulsive habit of imagining themselves at the center of things. For most of recorded history, the Earth was considered the fixed point around which everything else revolved: the sun, the moon, the planets, the stars. When Copernicus and Galileo dismantled that illusion, the adjustment was painful but survivable, because at least the sun was still special, still central, still something. Then came the discovery that the sun was an ordinary star in an ordinary part of an ordinary galaxy, and the galaxy itself was one among billions, and the cosmic demotion continued, step by step, century by century, each new discovery pushing humanity further from significance. The universe did not put us at the center. It did not put us anywhere in particular. We are orbiting a forgettable star in the unfashionable suburbs of a spiral galaxy that is itself drifting through a cosmos so vast that our entire galactic neighborhood, the local group of roughly 80 galaxies bound together by gravity, is a speck within the Virgo supercluster, which is itself a modest tendril in the Laniakea supercluster, which is itself a barely noticeable filament in the cosmic web, the vast three-dimensional lattice of matter that stretches across the observable universe like the neural network of some unimaginable brain. And between the filaments, between the threads of this cosmic web, lie the voids. Not small voids, not the modest emptiness of a quiet room or an abandoned building. Cosmic voids span hundreds of millions of light years across, volumes of space so enormous that light could not cross them in the entire history of human civilization multiplied 1,000-fold. The Boötes void, one of the largest known, stretches roughly 330 million light-years in diameter and contains almost nothing. A few dozen galaxies, perhaps, scattered through a volume that should hold thousands. If the Milky Way were located at the center of the Boötes void, humans would not have discovered the existence of other galaxies until the 1960s, because none would have been close enough to see with the telescopes available before then. We would have spent most of our scientific history believing that the Milky Way was all there was, a single island of light in an infinite ocean of darkness. We would have been wrong, but we would have had no way of knowing it, and the universe would not have corrected us. This is what the scale of the cosmos does to certainty. It erodes it. Every confident statement about the universe is bounded by what we can see, and what we can see is bounded by the speed of light and the age of space, and both of those boundaries may be hiding more than they reveal. The observable universe, vast as it is, may be an insignificant fraction of the total universe, which could be thousands or millions or infinitely many times larger. Some models of cosmic inflation suggest that the space generated during that first fraction of a second was so immense that the observable universe is to the total universe as a single atom is to the observable universe itself. If this is true, and it may be, then everything we have ever seen, every galaxy and every deep field image, every photon of the cosmic microwave background, every signal from every telescope ever built, is a rounding error in a cosmos so large that the human language has no word for it and the human mind has no category to place it in. When you look up at the night sky, you are not looking at the universe. You are looking at a thin shell of the past, a fraction of what exists, filtered through the limitations of light speed and human technology. The stars you see with your naked eye, roughly 5,000 on a clear night, are all within the Milky Way, most of them within a few hundred light years. You are seeing your immediate neighborhood, and even that neighborhood is full of ghosts. Some of the stars you admire tonight may have already burned out and collapsed. Their death light simply has not reached you yet. You are stargazing in a graveyard and mistaking the headstones for houses. And yet, for all its emptiness, for all its impossible distances and indifferent silences, the universe is not done revealing what it is made of. The stars and planets and gas and dust that you can see, everything that emits or reflects or absorbs light, everything that telescopes can detect, everything that feels solid and real and knowable, accounts for roughly 5% of the total content of the cosmos. 5%. The rest is something else, something that does not shine, does not reflect, does not interact with light in any way, something that permeates all of space and shapes the structure of everything you can see while remaining itself completely invisible. Call it the invisible architecture. Call it the skeleton beneath the skin of the cosmos, the scaffolding that holds up every galaxy and every cluster and every supercluster while refusing absolutely and stubbornly to be seen. For the better part of a century, physicists have known that the universe they can observe, the stars and gas and dust and planets, and all the luminous matter that telescopes were built to detect, is not nearly enough to explain how the cosmos behaves. The math does not work. The galaxies spin too fast. The clusters hold together too tightly. The large-scale structure of the universe, the cosmic web with its filaments and nodes and voids, could not have formed in the time available if ordinary matter were all there was. Something else is out there, something massive, something gravitationally powerful, something woven through every corner of space. And it does not emit light, absorb light, scatter light, or interact with light in any detectable way. It is, for all practical purposes, a ghost that weighs more than everything you have ever seen combined. The first person to notice the ghost was a Swiss astronomer named Fritz Zwicky, and he noticed it in 1933, which means that humanity has been aware of this problem for the better part of a century and has made distressingly little progress towards solving it. Zwicky was studying the Coma Cluster, a dense congregation of over 1,000 galaxies roughly 320 million light-years from Earth. He wanted to measure the total mass of the cluster, and he had two ways of doing it. The first was to add up all the light coming from the galaxies and use that to estimate how much luminous matter the cluster contained. The second was to measure how fast the individual galaxies were moving within the cluster and use their velocities to calculate how much gravitational mass was needed to hold them together. If the universe were straightforward, these two numbers would have agreed. They did not. They did not even come close. The galaxies in the Coma cluster were moving far too fast for the visible matter to account for. By Zwicky's calculations, the cluster needed roughly 400 times more mass than could be seen to prevent its galaxies from flying apart. 400 times. Not a small discrepancy. Not a rounding error. A factor of 400 which is the kind of number that either means your instruments are broken or your understanding of the universe is fundamentally incomplete. Zwicky proposed that the cluster must contain vast quantities of unseen matter, which he called dunkle materie, dark matter. His colleagues largely ignored him. Zwicky was a brilliant but abrasive man, known for calling people he disagreed with spherical bastards, on the grounds that they were bastards no matter which direction you looked at them. His personality did not win him allies, and his extraordinary claim about invisible mass was filed away as an oddity, a curiosity, a problem for someone else to deal with at some unspecified future date. That future date arrived in the 1970s, and the person who forced the issue was an American astronomer named Vera Rubin. Rubin was studying the rotation curves of spiral galaxies, which is a technical way of saying she was measuring how fast stars at different distances from the center of a galaxy were orbiting. The expectation, based on Newton's laws and the visible distribution of matter, was clear. Stars near the center, where most of the luminous mass was concentrated, should orbit quickly, while stars farther out, where the gravitational pull was weaker, should orbit more slowly. This is exactly how the solar system works. Mercury, the closest planet to the Sun, moves faster than Neptune, the farthest. The pattern is simple, intuitive, and, it turns out, completely wrong when applied to galaxies. What Rubin found, galaxy after galaxy, was that the rotation curves were flat. Stars at the outer edges of galaxies were orbiting just as fast as stars near the center, in some cases even faster. This should not have been possible. If the only matter in a galaxy were the matter you could see, the stars at the edges would have been moving so fast that they should have been flung out into intergalactic space like sparks from a grinding wheel. The galaxies should have torn themselves apart billions of years ago. The fact that they had not, the fact that they were sitting there calmly spinning in defiance of visible physics, meant that something invisible was holding them together. Something massive, something distributed in a vast halo extending far beyond the visible disk of stars, something that exerted gravitational force without emitting a single photon. Rubin had confirmed what Zwicky had suspected 4 decades earlier, and this time the scientific community could not ignore it. The data was too clean, too consistent, too devastating. Galaxy after galaxy showed the same flat rotation curve. The phenomenon was not a fluke confined to one odd cluster. It was universal. Every galaxy in the cosmos appeared to be embedded in a vast cloud of invisible matter that outweighed the visible stars by a factor of roughly 6 to 1. The universe was not what it appeared to be. The bright, shining objects that astronomers had spent centuries cataloging were, in terms of mass, a minority population, a scattering of luminous crumbs on a table made of something else entirely. And then came the lensing. Albert Einstein had predicted, in his General Theory of Relativity, published in 1915, that mass warps the fabric of spacetime, and that light traveling through warped spacetime would follow a curved path. The more massive the object, the greater the warping, and the more dramatically the light would bend. In 1979, astronomers observed the first gravitational lens, a distant quasar whose light was being bent around a massive galaxy sitting between the quasar and Earth, producing multiple images of the same object, like a cosmic funhouse mirror. The effect was elegant and strange, and it opened a new window onto the distribution of mass in the universe, because the amount of bending told you how much mass was doing the bending, regardless of whether that mass was visible. When astronomers began mapping the gravitational lensing caused by galaxy clusters, the results were unsettling. The lensing was far stronger than it should have been if the clusters contained only the matter that could be seen. Enormous arcs of distorted light smeared images of background galaxies bent into crescents and rings testified to vast quantities of mass that no telescope could detect. In some clusters, the lensing maps revealed a distribution of invisible mass that did not even align with the visible galaxies. The dark matter was there, its gravitational fingerprint unmistakable, but it was arranged according to its own logic, following a structure that had nothing to do with the bright objects that astronomers were accustomed to studying. The visible galaxies were not the main event. They were foam on the surface of an ocean they could not see. The Bullet Cluster, observed in 2006, provided what many physicists consider the most direct evidence for dark matter's existence. Two galaxy clusters had collided, passing through each other in a cosmic car crash that took millions of years to unfold. During the collision, the ordinary matter in the clusters, mostly hot gas, interacted and slowed down, piling up in the center like two clouds of steam colliding in midair. But the dark matter, whatever it was, did not interact. It passed straight through, like two crowds of ghosts walking through each other without noticing. Gravitational lensing maps showed the mass concentrated in two separate lobes, far from the hot gas in the center, exactly where you would expect it to be if it were made of particles that feel gravity but ignore everything else. The visible matter said one thing, the gravitational evidence said another, and the gravitational evidence won, because gravity does not lie, even when everything else is invisible. So what is dark matter? This is where the story becomes genuinely humbling, because the honest answer, after nearly a century of investigation and billions of dollars spent on some of the most sensitive detectors ever built, is that nobody knows. The leading candidates are particles that interact only through gravity and possibly the weak nuclear force, generically called WIMPs, short for weakly interacting massive particles. The idea is appealing because several extensions of the standard model of particle physics predict particles with exactly the right properties. And for decades, physicists were optimistic that a direct detection was imminent. Underground laboratories were built, deep beneath mountains in Italy and South Dakota and Canada, filled with tanks of liquid xenon and germanium crystals cooled to near absolute zero, all designed to catch the faint signal of a dark matter particle colliding with an ordinary atom. The experiments ran for years. The detectors grew more sensitive. The exclusion limits tightened. Nothing was found. Experiment after experiment returned null results, ruling out the most popular WIMP candidates one by one, narrowing the parameter space without ever finding a signal. Other candidates have been proposed. Axions, hypothetical ultralight particles originally invented to solve a different problem in particle physics. Sterile neutrinos, heavier cousins of the neutrinos already known to exist. Primordial objects formed in the earliest moments of the universe before ordinary matter had coalesced. Each candidate has its advocates, its theoretical elegance, its experimental program. None has been confirmed. The substance that makes up roughly 27% of the total mass-energy content of the universe, the substance that shaped the formation of every galaxy and holds them together to this day, remains, as of this moment, completely unidentified. We know it is there. We can see its effects. We can map its distribution. We can simulate its behavior on supercomputers. We simply do not know what it is. And dark matter, for all its mystery, is not even the strangest part of the story. In 1998, two independent teams of astronomers set out to measure how quickly the expansion of the universe was slowing down. The question was not whether it was slowing. That was considered a given. The universe had been expanding since its birth, and gravity, the attractive force between all matter, should have been gradually pulling on that expansion like a brake, decelerating it over time. The only question was how fast the deceleration was happening, because the answer would reveal the ultimate fate of the cosmos. Would it slow to a halt and collapse back on itself? Or would it coast to a gentle stop and drift into a cold, static eternity? Both teams used Type Ia supernovae as cosmic measuring sticks. These are a particular kind of stellar explosion, the thermonuclear detonation of a white dwarf star that has accumulated too much matter from a companion, and they are useful because they all explode with roughly the same intrinsic brightness. If you know how bright something truly is, and you measure how bright it appears, you can calculate how far away it is. And if you also measure how much the light has been stretched by the expansion of space, redshifted into longer wavelengths, you can determine how fast the universe was expanding at the time the light was emitted. By observing supernovae at different distances, and therefore different points in cosmic history, the teams planned to chart the expansion rate over time and watch it slow down. The first team was led by Saul Perlmutter at the Lawrence Berkeley National Laboratory. The second was led by Brian Schmidt at the Australian National University, with Adam Rees handling much of the data analysis. They worked independently, used different telescopes, employed different analysis methods, and checked each other's work with the skepticism that comes naturally to scientists who know that extraordinary claims require extraordinary evidence. And then, within weeks of each other, they arrived at the same conclusion. The expansion of the universe was not slowing down. It was speeding up. The distant supernovae were dimmer than expected, meaning they were farther away than expected, meaning the expansion of the universe had been accelerating, not decelerating, for the past several billion years. Something was pushing the cosmos apart, something that worked against gravity, something that operated on the largest scales and grew stronger as space itself expanded. The result was so unexpected that both teams initially assumed they had made a mistake. They checked the data again. They checked it a third time. They accounted for dust, for calibration errors, for every known systematic bias. The result held. The universe was accelerating, and nothing in the existing framework of physics could explain why. The name given to this unknown force was dark energy, a label that communicates almost nothing about what it actually is. The name is a placeholder, a two-word confession of ignorance dressed up as terminology. Dark energy is not energy in the way that heat or light or kinetic motion is energy. It is not dark in the way that a room with the lights off is dark. It is dark in the sense of unknown, and energy in the sense that it has to be called something, and the community settled on a term that would at least fit on a conference slide. What is known about dark energy can be stated briefly, and the brevity is itself a measure of how little is understood. It accounts for approximately 68% of the total mass energy content of the universe. It appears to be a property of space itself, a kind of intrinsic pressure or repulsive tendency woven into the vacuum that causes the expansion of space to accelerate. It does not cluster. It does not dilute as space expands. It is uniform, constant, and relentless. And its existence was, in a cruel twist of intellectual history, predicted and then discarded decades before it was discovered. When Einstein first applied his general theory of relativity to the universe as a whole in 1917, he found that his equations predicted a universe that was either expanding or contracting. This troubled him. The prevailing view at the time was that the universe was static, eternal, and unchanging, and Einstein, for all his revolutionary brilliance, was a man of his era. Rather than accept what his own equations were telling him, he introduced a fudge factor, a term he called the cosmological constant, represented by the Greek letter lambda. which provided a repulsive force to balance gravity and keep the universe perfectly still. It was an elegant mathematical fix with no physical justification, and Einstein knew it was ugly. When Edwin Hubble demonstrated in 1929 that the universe was in fact expanding, Einstein reportedly called the cosmological constant his biggest blunder and abandoned it. 70 years later, the cosmological constant came back from the dead. The accelerating expansion discovered in 1998 behaved almost exactly the way Einstein's discarded lambda would predict. The cosmological constant, it seemed, was not a blunder after all. It was a prophecy. Einstein had the right answer for the wrong reason, introduced it to solve a problem that did not exist, and threw it away just before the real problem it described was discovered. The universe, it appears, has a sense of irony, but saying that dark energy is the cosmological constant does not explain it. It merely gives it a name and a mathematical description. The deeper question, what generates this repulsive energy, why it has the value it does, and why it exists at all, remains unanswered. The value of the cosmological constant is, by the standards of particle physics, absurdly small. When theorists attempt to calculate what the vacuum energy of space should be based on quantum field theory, they get a number that is larger than the observed value by a factor of 10 to the power of 120. That is not a small discrepancy. It is the largest disagreement between theory and observation in the history of physics, so large that it has its own name, the cosmological constant problem. The fact that the vacuum energy is not zero is surprising. The fact that it is not the enormous value predicted by quantum theory is baffling. The fact that it happens to have precisely the value needed to accelerate the expansion at the rate we observe, neither too large to have torn the universe apart before galaxies could form, nor too small to have no effect, is, depending on your temperament, either a profound clue or a profound coincidence. Step back for a moment and take in the full picture. Of everything in the universe, all the mass and energy in every form, roughly 68% is dark energy, a force that no one understands. Roughly 27% is dark matter, a substance that no one has identified. And the remaining 5% is ordinary matter, the atoms, the protons and neutrons and electrons, the stuff of stars and planets and human bodies, and everything ever studied in every chemistry lab and physics department on Earth, 5%. The entirety of what humans have ever directly observed, ever touched, ever measured, ever built anything out of, accounts for 1/20th of the cosmos. The other 19/20ths are invisible, unexplained, and operating according to rules that have not been written down. You are living in a house where you can see one room. The other 19 rooms are locked, and you do not have the keys, and you are not entirely sure the house has doors. The Vera C. Rubin Observatory, currently under construction in Chile and expected to begin full survey operations in the coming years, is designed in part to map dark matter and dark energy with unprecedented precision, using gravitational lensing on a scale never before attempted. It will observe roughly 20 billion galaxies over 10 years, cataloging their shapes, their distortions, and the invisible mass that bends their light. The European Space Agency's Euclid mission, launched in 2023, is performing a complementary survey from orbit, mapping the geometry of the universe across 10 billion years of cosmic history to trace how the expansion rate has changed over time. These are not small projects. They represent the combined effort and budget of thousands of scientists across dozens of countries, aimed at answering a question that should, by all rights, be embarrassing. What is the universe made of? The fact that we do not know nearly a century after Zwicky first pointed at the coma cluster and said something was missing, is either a testament to the difficulty of the problem or a testament to the limitations of a species that has been doing science for only a few hundred years on a planet that has been habitable for a few billion. Either way, the implication is the same. The universe you can see, the universe of stars and light and color and spectacle, is a thin veneer painted over a structure you cannot perceive. The real universe, the one that accounts for 95% of everything, operates in total darkness by rules that have never been observed, made of substances that have never been touched, and it has been doing this since long before your species learned to walk upright. The cosmos is not merely larger than you thought. It is more opaque than you thought. The cosmos is not merely larger than you thought. It is more opaque than you thought. You are not standing on solid ground, looking out at a well-lit landscape and mapping its features. You are standing on a platform that you cannot see, suspended over a chasm whose depth you cannot measure, in a building whose walls you cannot find. And the 5% of reality that you can perceive, the sliver of the cosmos that interacts with your instruments and your senses, contains within it objects so extreme, so violently warped, so fundamentally alien to everyday experience, that they break the very laws of physics that describe everything else. Picture a man sitting in a trench on the Eastern Front in the winter of 1915, with artillery shells turning the frozen ground into mud and shrapnel around him, working out the geometry of the end of the world. Karl Schwarzschild was a German physicist and astronomer who had volunteered for military service at the age of 42, and he was, by all accounts, not the sort of person you would expect to find calculating the curvature of spacetime while dodging Russian ordnance. He had read Einstein's freshly published General Theory of Relativity, which described gravity not as a force, but as the warping of spacetime by mass. And within weeks, he had done something Einstein himself had not managed. He had found an exact solution to the field equations for the case of a perfectly spherical, non-rotating mass. The solution was elegant, compact, and contained within it a prediction so disturbing that Schwarzschild himself may not have fully appreciated what he had uncovered. At a certain radius from the center of any sufficiently massive object, the mathematics produced a boundary, a surface of no return, where the escape velocity equaled the speed of light. Anything that crossed this boundary, any object, any signal, any photon of light, could never come back. The boundary would later be called the event horizon. The object it described would later be called a black hole. Schwarzschild sent his solution to Einstein from the front. He died 4 months later, likely from a rare autoimmune disease contracted in the trenches, never knowing that his mathematics had described one of the most terrifying objects in the universe. The idea of an object so dense that light could not escape it was not entirely new. An English clergyman and natural philosopher named John Michell had proposed the concept in 1783, reasoning from Newtonian gravity that a star sufficiently massive and compact would have an escape velocity exceeding the speed of light, rendering it invisible. He called these hypothetical objects dark stars, and the idea was largely forgotten for more than a century, filed alongside countless other clever speculations that lacked the mathematical framework to make them testable. What Schwarzschild's solution provided was that framework, embedded in the most accurate theory of gravity ever devised, and the framework said that dark stars were not merely possible. They were, under the right conditions, inevitable. The conditions are, in fact, remarkably straightforward. Take a star, let it exhaust its nuclear fuel. If the remnant core is massive enough, roughly 3 times the mass of the Sun or more, no known force in physics can prevent its collapse. The electrons cannot push back hard enough. The neutrons cannot push back hard enough. The degeneracy pressure that holds up white dwarfs and neutron stars is simply insufficient against the weight of the material pressing inward. And so the matter collapses, falling inward at a significant fraction of the speed of light, past the point where it could form a white dwarf, past the point where it could form a neutron star, past the event horizon, and into a region of space where the density becomes infinite, the volume becomes zero, and the laws of physics as currently understood cease to give sensible answers. This region is called the singularity, and it is not a place in any meaningful sense. It is a point where the mathematics of general relativity produces infinities, which in physics is usually a polite way of saying the theory has broken and something unknown is happening. The Indian-American astrophysicist Subramanian Chandrasekhar worked out the upper mass limit for white dwarf stars in 1930, showing that above approximately 1.4 solar masses, electron degeneracy pressure could not support the star against gravitational collapse. He was 20 years old and traveling by ship from India to Cambridge when he completed the calculation. When he presented his findings to the Royal Astronomical Society, the eminent Sir Arthur Eddington publicly ridiculed him, declaring that nature could not possibly allow such absurd outcomes. Chandrasekhar was right. Eddington was wrong. But it would take decades for the community to fully accept the implication that sufficiently massive stars at the end of their lives have nowhere left to go but down. In 1939, J. Robert Oppenheimer, who would shortly become famous for rather different reasons, co-authored a paper demonstrating that a sufficiently massive neutron star would undergo continued gravitational collapse, contracting past its Schwarzschild radius and forming what we now call a black hole. The paper was largely ignored at the time, partly because the prediction seemed too exotic to be taken seriously, and partly because the world was about to be otherwise occupied. It would take another 3 decades before the American physicist John Wheeler, in 1967, coined the term black hole, giving the concept a name vivid enough to capture the public imagination and sinister enough to hint at what the mathematics actually described. What the mathematics describes is an object that does not merely bend light, it ends it. At the event horizon, the curvature of spacetime becomes so extreme that all possible paths, every trajectory that any particle or photon could take, point inward. Not most paths, all of them. The event horizon is not a physical surface. It is not a wall or a membrane or a shell. It is a boundary in the geometry of space-time itself, a point of no return defined not by material, but by the shape of the universe in that region. Once you cross it, the singularity is no longer a place in space ahead of you. It is a moment in your future, as unavoidable as next Thursday. You could fire your engines at full thrust in any direction, and you would still reach the singularity, just as you cannot avoid tomorrow no matter which direction you walk. Time and space, inside the event horizon, have effectively swapped roles. Moving toward the singularity is no longer a spatial journey. It is the passage of time, and time, as everyone knows, only moves in one direction. But before you reach the singularity, assuming you are falling into a stellar mass black hole, something else will happen to you, and it will be deeply unpleasant. The gravitational pull of a black hole is not uniform. It is stronger at points closer to the singularity and weaker at points farther away. If you were falling, feet first, the gravitational force on your feet would be significantly stronger than the force on your head, and this difference, called a tidal force, would stretch you, not gently, not gradually. The stretching would increase as you fell, pulling you longer and thinner, your body drawn out like warm glass, your bones separating, your tissues tearing, your atoms eventually ripped apart as the tidal gradient became infinite. Physicists With the dark humor that characterizes a profession accustomed to contemplating catastrophe, call this process spaghettification. You would be turned into a long, thin strand of matter spiraling into the abyss, and the last signals you emitted, the last photons of light reflected from your increasingly elongated body, would be redshifted into invisibility as they struggled against the curvature of spacetime, dimming and stretching and dimming again until they vanished entirely. To an observer watching from a safe distance, your death would look even stranger. Because of the extreme time dilation near the event horizon, predicted by general relativity, the observer would see you appear to slow down as you approached the boundary. Your movements would become sluggish, your light growing dimmer and redder, your image frozen in an ever more distorted tableau that would never quite disappear but would fade asymptotically toward invisibility. The observer would never see you cross the event horizon. As far as they could tell, you would hover at the edge forever, growing fainter and fainter, a ghost imprinted on the surface of the abyss. From your perspective, of course, you would cross the horizon without noticing anything special, because locally, space-time at the event horizon is perfectly smooth. You would simply find, moments later, that there was no way back, that every direction led inward, and that the singularity was waiting. The question of what happens at the singularity itself is one of the genuine open wounds in physics. Roger Penrose, in the 1960s, proved mathematically that singularities are unavoidable inside black holes, that once an event horizon forms, the collapse to a point of infinite density is guaranteed by the equations of general relativity. He shared the 2020 Nobel Prize in Physics for this work 60 years after he did it, a delay that says something about how long it takes the world to properly acknowledge ideas that are both brilliant and deeply uncomfortable. But Penrose's theorem also highlighted a problem. General relativity predicts the singularity, and general relativity breaks down at the singularity. The theory predicts its own failure. At the center of every black hole, the equations that describe the rest of the universe produce nonsensical answers, infinities piled on infinities. And the consensus among physicists is that these infinities are not physically real, but are instead signals that a deeper theory, a theory of quantum gravity that unifies general relativity with quantum mechanics, is needed. That theory does not yet exist. Until it does, the interior of a black hole remains, in the most literal sense, beyond the reach of human understanding. And then Stephen Hawking made things worse. In 1974, Hawking published a paper that combined quantum mechanics with the physics of black holes, and the result was one of the most startling predictions in the history of theoretical physics. Quantum mechanics dictates that empty space is not truly empty. It seethes with virtual particles, pairs of matter and antimatter that pop into existence and annihilate each other in intervals so brief that they cannot be directly observed. At the event horizon of a black hole, Hawking showed something unusual happens. One particle from a virtual pair can fall into the black hole while the other escapes into space. The escaping particle carries energy away from the black hole, and because energy and mass are equivalent, the black hole loses a tiny amount of mass with each escaped particle. Over time, this process, now called Hawking radiation, causes the black hole to shrink. And if given long enough, with no new matter falling in to replenish it, the black hole will eventually evaporate entirely, disappearing in a final burst of radiation. The timescales involved are almost comically long. A black hole with the mass of the Sun would take roughly 10 to the power of 67 years to evaporate, a number so large that writing it out would fill several lines, and reading it would fill a lifetime of confused blinking. For the supermassive black holes at the centers of galaxies, the timescale stretches to 10 to the power of 100 years, a duration so vast that the current age of the universe is to it as a single atom is to the observable cosmos. But the principle stands. Black holes are not eternal. They are temporary. They are born, they feed, and eventually, in the unimaginably distant future, they die. The problem is, what happens to the information? In physics, information is not a metaphor. It is a precisely defined quantity, the complete description of a physical system's state. And one of the foundational principles of quantum mechanics is that information is never destroyed. It can be scrambled, encoded, transformed beyond recognition, but it cannot be erased. The equations of quantum mechanics are reversible. Given a system's current state, you can, in principle, reconstruct its entire history. But if a black hole swallows a book and then evaporates via Hawking radiation, what happens to the information contained in that book? Hawking's original calculation suggested that the radiation emitted by a black hole is purely thermal, perfectly random, carrying no information about what fell in. If this were true, it would mean that black holes destroy information, violating one of the most fundamental principles in all of physics. This is the black hole information paradox, and it has consumed theoretical physics for 5 decades. Hawking initially argued that information was indeed lost, a position that put him at odds with nearly every other major figure in the field. He later conceded, in 2004, that information is probably preserved, somehow, encoded in the Hawking radiation in a way that is not yet understood. But "not yet understood" is a phrase that does a great deal of work in this sentence, because the mechanism by which information escapes a black hole, if it escapes at all, remains one of the deepest unsolved problems in theoretical physics. Some physicists have proposed that information is encoded on the event horizon itself, like data stored on the surface of a hard drive, a concept known as the holographic principle. Others have invoked exotic structures called firewalls, surfaces of extreme energy at the event horizon that would incinerate anything that crosses them, thereby preserving information at the cost of contradicting general relativity's prediction that the horizon is smooth and unremarkable. Still others have suggested that the interior of a black hole is connected to other regions of spacetime through wormholes. Einstein-Rosen bridges that thread information out through the back door of the universe. None of these proposals has been proven. All of them are speculative. And the information paradox sits at the exact intersection of general relativity and quantum mechanics, the two pillars of modern physics that have never been successfully combined, which means that solving it may require a revolution in understanding comparable to the one Einstein himself initiated more than a century ago. While theorists argued about what happens inside black holes, observational astronomers were busy proving that the universe is absolutely riddled with them. The first strong candidate for a stellar mass black hole, Cygnus X1, was identified in 1971 as a powerful source of X-rays in the constellation Cygnus. A massive blue supergiant star was orbiting an invisible companion, and material being stripped from the star and spiraling into the companion was being heated to millions of degrees, emitting X-rays as it fell. The invisible companion was too massive to be a neutron star and too compact to be anything else. It was, almost certainly, a black hole, and Hawking famously bet his colleague Kip Thorne that it was not, a bet he cheerfully conceded in 1990 when the evidence became overwhelming. Since then, black holes have been found in droves. Stellar mass black holes, formed from the collapse of massive stars, populate every galaxy. But the truly staggering discovery was that nearly every large galaxy in the universe harbors a supermassive black hole at its center, an object millions or billions of times the mass of the Sun, sitting in the gravitational heart of the galaxy like a spider at the center of a web. The Milky Way's own supermassive black hole, called Sagittarius A star, has a mass of roughly 4 million solar masses and sits roughly 26,000 light-years from Earth, at the very center of the galaxy around which everything else orbits. It is, by the standards of supermassive black holes, modest. The black hole at the center of the galaxy Messier 87, known as M87 star, has a mass of roughly 6.5 billion solar masses, a number so large that the event horizon alone is larger than our entire solar system. In April of 2019, the Event Horizon Telescope collaboration released the first image of a black hole, and the object they chose was M87 star. The image was not taken by a single telescope. It was assembled from data collected by 8 radio telescopes spread across the globe, from Hawaii to Chile to the South Pole, all synchronized to observe the same target at the same time, effectively creating a virtual telescope the size of the Earth. The resulting image showed a ring of superheated gas swirling around a dark central shadow, the silhouette of the event horizon against the glowing accretion disk behind it. It was blurry, orange, and slightly lopsided, and it was also the most important astronomical image since the Hubble Deep Field, because it showed, for the first time, the shadow of the place where light ends. 2 years later, in 2022, the collaboration released an image of Sagittarius A star, our own galaxy's central black hole, confirming that the Milky Way, too, is anchored by an abyss. How these supermassive black holes formed is not entirely clear. Stellar mass black holes form from dying stars, but a 4 million solar mass black hole cannot be built by simply merging a few dead stars together. Something more dramatic must have happened in the early universe. Perhaps the direct collapse of enormous gas clouds, perhaps the rapid merging of many smaller black holes in the dense cores of primordial galaxies, perhaps something else entirely. The James Webb Space Telescope has discovered supermassive black holes that appear to have existed when the universe was less than 1 billion years old, which is uncomfortably early, suggesting that either these objects grew far faster than current models predict, or they formed through mechanisms that have not yet been imagined. The universe, as usual, is ahead of the theorists. And then, on the 14th of September, 2015, the universe spoke in a voice no one had ever heard before. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, consists of 2 enormous detectors, one in Livingston, Louisiana, and one in Hanford, Washington, each built around an L-shaped vacuum tunnel roughly 4 kilometers long. Laser beams are bounced between mirrors at the ends of the tunnels, and the system is sensitive enough to detect changes in the length of the tunnels of less than 1/10,000th the diameter of a proton. On that September morning, both detectors registered a signal, a brief chirp lasting less than a second, in which the frequency rose rapidly before cutting off abruptly. The chirp was the gravitational wave signature of 2 black holes, one roughly 36 solar masses and the other roughly 29, spiraling toward each other at nearly the speed of light and merging into a single black hole of roughly 62 solar masses. The missing 3 solar masses had been converted into pure gravitational radiation, ripples in the fabric of spacetime itself, which expanded outward at the speed of light and, 1.3 billion years later, passed through the Earth, flexing the tunnels of the LIGO detectors by an amount smaller than the nucleus of an atom. The detection was announced in February of 2016. and the three physicists most responsible for LIGO's development, Rainer Weiss, Kip Thorne, and Barry Barish, were awarded the 2017 Nobel Prize in Physics. But the prize, and the press conferences, and the champagne toasts obscured what the detection actually meant, which was this: for the first time in history, humanity had perceived the universe not through light, but through gravity. The chirp that LIGO recorded was, when converted to an audio frequency, audible to the human ear, a sound that rises in pitch like a whistle and then stops, the sound of two objects so massive that their collision shook the fabric of reality across 1.3 billion light-years of space. Scientists have since recorded dozens of such events: black holes colliding with black holes, neutron stars colliding with neutron stars, and at least one case of a black hole swallowing a neutron star, each event producing its own gravitational signature, its own ripple in the cosmic pond. The universe, it turns out, is not silent. It has been ringing like a bell for 13.8 billion years. We simply lacked the ears to hear it. What gravitational wave astronomy has revealed, among other things, is that the universe is full of violence that produces no light. Black hole mergers, by definition, emit no electromagnetic radiation from the merger itself, because nothing escapes the event horizon. Before LIGO, these events were invisible, undetectable, happening in the dark between the stars without anyone's knowledge. Now we know they happen constantly, throughout the cosmos, black holes finding each other across the void, spiraling together over millions of years, and then, in a final fraction of a second, colliding with a force that briefly outshines, in gravitational wave energy, every star in the observable universe combined. The cosmos is not just vast and mostly empty. It is vast and mostly empty and full of invisible catastrophes happening in a register that human senses were never built to perceive. And yet, for all their strangeness, black holes are at least objects. They have mass, they have spin, they have a location. They obey, in all their external behavior, the laws of physics. They can be modeled, simulated, photographed, and heard. The next terror on the cosmic menu is less accommodating. It has no location, no mass, no spin. It is not an object at all. It is a possibility, a latent instability in the ground state of reality. And if it is real, it is the most destructive force the universe has ever produced or ever will produce, because its destruction is total, traveling at the speed of light and carrying no warning whatsoever. But that particular nightmare, the instability lurking in the fabric of the vacuum, belongs to another part of this story. Set it aside for now. Set aside the abysses that swallow light, the invisible scaffolding that outweighs everything you can see, the distances that mock the speed of light itself. Set all of it aside, because the cosmos has one more trick, one more turn of the screw, and it is not an object or a force or a catastrophe. It is an absence. It is the thing that should be here and is not. It is the dog that did not bark. And in many ways, it is the most unsettling discovery that human beings have ever failed to make. The summer of 1950 was hot in Los Alamos, New Mexico. Enrico Fermi, the Italian-born physicist who had built the world's first nuclear reactor beneath the bleachers of a squash court in Chicago, who had helped design the weapon that ended the Second World War, who was widely regarded as one of the finest scientific minds of the 20th century, was walking to lunch with three colleagues, Edward Teller, Herbert York, and Emil Konopinski. The conversation, as it often did among physicists at Los Alamos, wandered freely. Someone brought up a recent cartoon in The New Yorker that had depicted aliens stealing dustbins from a New York sidewalk, which led to a joking discussion about flying saucers, which led to a more serious discussion about interstellar travel, which led, in the way that conversations between very smart people sometimes do, to a question so simple and so devastating that it has haunted science for 3/4 of a century. Fermi, halfway through his lunch, looked up from his plate and said, "But where is everybody?" His colleagues laughed. Then they stopped laughing, because they realized that the question, for all its casualness, had no good answer. The logic was straightforward, almost childishly simple. The Milky Way is old, roughly 13 billion years old. It contains hundreds of billions of stars, many of them billions of years older than the Sun. If even a small fraction of those stars have planets, and even a small fraction of those planets develop life, and even a small fraction of that life develops intelligence, and even a small fraction of that intelligence develops technology, then the galaxy should be teeming with civilizations far older and far more advanced than ours. Some of those civilizations should have developed the ability to travel between stars, or at least to send signals across interstellar distances, even at speeds far below the speed of light, using technologies that are conceivable with current physics. A single civilization could colonize the entire galaxy in a few tens of millions of years, a blink of an eye in cosmic time. The galaxy should be buzzing with activity, saturated with signals, crisscrossed with the traffic of 1,000 spacefaring species. And yet, when we look up, we see nothing. When we listen, we hear nothing. Every frequency, every wavelength, every corner of the electromagnetic spectrum that we have ever scanned has returned the same answer: silence. No signals, no probes, no megastructures. No evidence of engineering on any scale, anywhere, ever. The universe is not just quiet. It is aggressively, conspicuously, almost performatively empty. This is the Fermi Paradox, and it is not, despite its name, a paradox in the strict, logical sense. It is a contradiction between a reasonable expectation and an observed reality. The reasonable expectation is that intelligent life should be common. The observed reality is that we have found no trace of it anywhere despite decades of searching. Something in the chain of reasoning must be wrong. Some assumption must be flawed. Some factor must be missing, and the possible explanations for what that factor might be range from the comforting to the catastrophic. Before Fermi asked his question, though after the question was already implicit in the data, a young American astronomer named Frank Drake sat down in the autumn of 1961 at the Green Bank Observatory in West Virginia and tried to put numbers to the problem. Drake was preparing for a small conference on the search for extraterrestrial intelligence, and he wanted a framework for organizing the discussion. What he produced was not an equation in the usual scientific sense, not a formula that could be solved with known values to produce a definitive answer. It was a way of thinking, a structured list of the factors that would determine how many communicating civilizations might exist in the galaxy at any given time. The Drake equation, as it came to be known, multiplied together 7 terms: the rate of star formation in the galaxy, the fraction of those stars that have planets, the number of planets per star that could support life, the fraction of those planets where life actually develops, the fraction of life-bearing planets where intelligence evolves, the fraction of intelligent civilizations that develop technology capable of sending detectable signals, and the average length of time such civilizations continue to transmit. Multiply all 7 terms together, and you get N, the number of detectable civilizations in the galaxy right now. The beauty of the equation is that it is logically airtight. Every term matters, and every term is a real quantity that, in principle, could be measured. The horror of the equation is that, in 1961, almost none of the terms were known. Drake and his colleagues were guessing, and their guesses ranged wildly. Optimists, plugging in generous values for each term, arrived at numbers in the thousands or millions, a galaxy humming with intelligence. Pessimists, plugging in conservative values, arrived at numbers close to 1, a galaxy in which Earth is alone. The equation did not resolve the debate. It clarified the shape of the ignorance. In the decades since, some of the early terms have been nailed down. The rate of star formation is well measured. The fraction of stars with planets has been revolutionized by the Kepler Space Telescope, launched in 2009, which discovered that planets are not rare at all but staggeringly common, with most stars in the galaxy hosting at least one planet, and a significant fraction hosting rocky planets in the habitable zone, the orbital region where liquid water could exist on the surface. The first 3 terms of the Drake equation, once wildly uncertain, now point in a single direction. The raw materials for life are everywhere. Planets that could support life are not exceptional. They are ordinary. The Milky Way alone contains billions of them, which makes the silence worse. If habitable planets are common, and no one is broadcasting, then something must be stopping life from reaching the point where it builds radio telescopes and says hello. This is the concept of the Great Filter, proposed by the economist Robin Hanson in 1998, and it is the idea that keeps astrobiologists up at night. The Great Filter is a hypothetical stage in the development of life at which the probability of advancing to the next stage is essentially 0. A bottleneck so severe that virtually no civilization passes through it. The critical question, the one with implications that split neatly into hope and despair, is whether the Great Filter is behind us or ahead of us. If the Great Filter is behind us, then the hard part is already done. Perhaps the origin of life itself is so improbable that it has only happened once. Perhaps the leap from single-celled to multicellular organisms is the bottleneck, or the development of eukaryotic cells, or the evolution of intelligence, or any of the dozens of transitions that had to occur on Earth for a species capable of asking this question to emerge. If the filter is behind us, we are special. We are the ones who made it through. We are rare, possibly unique, and the silence of the cosmos is simply the sound of an empty galaxy waiting for its first civilization to spread. This is the optimistic interpretation, and it carries a weight of loneliness that is difficult to exaggerate, but it is at least a loneliness without threat. If the Great Filter is ahead of us, the picture changes entirely. If the filter is ahead of us, then life may be common, intelligence may be common, technological civilizations may arise regularly across the galaxy, and every single one of them is destroyed before it can make its presence known. Every one, without exception. The silence of the cosmos is not the sound of emptiness. It is the sound of a graveyard. It is the sound of 1,000 civilizations reaching for the stars and being annihilated by something they did not see coming or could not prevent or brought upon themselves. And if this is true, then whatever killed them is waiting for us too, and we are walking toward it with all the confidence of a species that has never encountered it before. This is why the discovery of microbial life on Mars or Europa or Enceladus, which most people would greet with excitement and wonder, is viewed by certain scientists with something closer to dread. Every piece of evidence that life arises easily is evidence that the Great Filter is not the origin of life. If the filter is not at the beginning, it must be further along, which means it is more likely to be ahead of us. Finding a galaxy full of microbes and empty of civilizations would be the most terrifying discovery in human history, because it would mean that something consistently destroys technological species, and we do not know what it is, and we are one. The explanations for the silence, beyond the Great Filter, are numerous, creative, and in many cases deeply unsettling. One of the earliest was the zoo hypothesis. proposed by the MIT radio astronomer John Ball in 1973. Ball suggested that advanced civilizations are aware of us but deliberately avoid contact, treating Earth as a nature reserve or a zoo, observing without interfering, the way a wildlife biologist might watch a troop of chimpanzees without announcing her presence. The hypothesis is unfalsifiable, which is its strength as a thought experiment and its weakness as science, because you cannot prove the absence of watchers. But it has a certain plausibility if you accept that any civilization old enough and advanced enough to reach us would also be wise enough to recognize the damage that contact could cause. After all, the history of contact between unequal civilizations on Earth has rarely gone well for the less advanced party. A darker variation is the dark forest theory, popularized by the Chinese science fiction author Liu Cixin in his novel of the same name, published in 2008. The dark forest theory begins with two axioms. First, that survival is the primary need of every civilization, and second, that civilizations continuously grow and expand, while the total resources of the cosmos are finite. From these axioms, Liu constructs a chilling game-theoretic argument. In a universe where communication is slow and trust is impossible to verify, the safest strategy for any civilization that detects another is to destroy it immediately, before it has a chance to grow into a threat. You cannot know whether a newly discovered civilization is peaceful or hostile, and by the time you find out, it may be too late. The rational move, the move that natural selection would favor among competing civilizations, is to strike first and ask questions never. The universe, in this model, is a dark forest in which every civilization is a silent hunter moving through the trees with its weapon raised, knowing that any sound, any signal, any evidence of its existence could bring annihilation from a direction it cannot see. The dark forest theory carries a corollary that should give pause to anyone who has ever been enthusiastic about broadcasting humanity's presence to the stars. In 1974, the Arecibo Observatory in Puerto Rico transmitted a coded message toward the globular cluster Messier 13, roughly 22,000 light-years away. The message, designed by Frank Drake and the astronomer Carl Sagan, among others, contained information about human DNA, the solar system, and the population of Earth, encoded in a pattern of ones and zeros that any sufficiently intelligent recipient could decode. It was an act of optimism, a greeting tossed into the cosmic ocean like a bottle with a note inside. If the dark forest theory is correct, it was also an act of staggering recklessness, a creature in a forest full of predators standing up and shouting its location. The message will not arrive at Messier 13 for another 22,000 years, and any reply would take an equal amount of time to return. So the consequences of the Arecibo message are not an immediate concern. But the principle it represents, the deliberate transmission of information about Earth's location and its inhabitants into a universe whose intentions are unknown, has generated genuine debate among scientists. Stephen Hawking, before his death in 2018, warned publicly against attempting to contact extraterrestrial civilizations, arguing that the outcome could resemble what happened when Native Americans encountered Columbus. Others have argued that the concern is overblown, that any civilization capable of reaching us would already know we are here, our atmosphere having advertised the presence of life through its oxygen content for billions of years. The debate remains unresolved, in part because it hinges on the motivations and psychology of beings that may not exist, which makes it, in the strictest sense, an argument about nothing. And then there is the wow signal, which is the closest thing the search for extraterrestrial intelligence has ever produced to a genuine mystery, and which remains, after nearly half a century, unexplained. On the 15th of August, 1977, a volunteer astronomer named Jerry Eman was reviewing data from the Big Ear Radio Telescope at Ohio State University, which was conducting a survey of the sky as part of the SETI program, the ongoing scientific effort to detect signals from extraterrestrial civilizations. The telescope scanned the sky passively, recording the intensity of radio signals across a narrow band of frequencies centered on the hydrogen line at 1,420 megahertz, a frequency considered a natural choice for interstellar communication because hydrogen is the most abundant element in the universe, and any technologically capable species would know its emission frequency. As Eamon reviewed the printout, a long scroll of numbers representing signal strength, one sequence leapt off the page. For 72 seconds, the telescope had recorded a signal that was 30 times stronger than the background noise, narrowband, exactly at the hydrogen frequency, and coming from the direction of the constellation Sagittarius. Eamon circled the sequence on the printout and wrote a single word in the margin: "Wow." The signal had all the characteristics that SETI researchers had predicted an artificial extraterrestrial signal would have. It was narrow in frequency, unlike natural radio sources, which tend to be broadband. It was strong, far stronger than any known natural source in that part of the sky. It appeared to come from a fixed point in space, consistent with a distant transmitter, and its 72-second duration matched exactly the window of time that the Big Ear telescope would observe a fixed point as the Earth's rotation swept the antenna across the sky. It was, in short, precisely what an alien signal was supposed to look like, and it never repeated. The Big Ear telescope observed the same region of sky more than 100 times in the months and years that followed. Other telescopes were pointed at the same coordinates. Nothing was ever detected again. The signal appeared once, for 72 seconds, and then vanished, leaving behind nothing but a circled sequence of characters on a printout and a question that has never been answered. Explanations have been proposed. A comet, releasing hydrogen gas, could theoretically produce a narrowband signal at the hydrogen frequency, and in 2017, an astronomer proposed that a pair of comets known to have been in the approximate region of sky might be the source. The hypothesis was widely disputed, and subsequent analysis found it unconvincing. Others have suggested terrestrial interference, a signal reflected off space debris, or an instrumental artifact. But none of these explanations comfortably accounts for all the characteristics of the signal. The honest assessment, the one that most scientists will offer if pressed, is that nobody knows what the wow signal was. It remains an anomaly, a single data point with no context, a whisper in a silent room that was never repeated and never explained. The SETI program itself has evolved considerably since Eamon's night at the Big Ear. Project Ozma, the first modern SETI experiment, was conducted by Frank Drake in 1960 at Green Bank, targeting just two nearby stars, Tau Ceti and Epsilon Eridani, with a single-channel receiver. Nothing was detected. Since then, the search has expanded enormously in scope and sensitivity. The Allen Telescope Array in Northern California, funded in part by Microsoft co-founder Paul Allen, was designed specifically for SETI and began observations in 2007. Breakthrough, listen, launched in 2015 with $100 million in funding from the Russian-Israeli investor Yuri Milner, is the most comprehensive SETI program ever undertaken, surveying the 1 million nearest stars and the 100 nearest galaxies across a wide range of frequencies. The sensitivity of these instruments is orders of magnitude beyond anything available in the 1970s. The sky coverage is broader. The analysis software is more sophisticated. The result has been the same. Silence. 65 years of listening. thousands of stars surveyed, billions of frequency channels scanned, and not one confirmed artificial signal from beyond the Earth. Not one. The universe remains as mute as it was the day Fermi asked his question over lunch, and the fact that our instruments have grown millions of times more sensitive without detecting anything has, if anything, made the paradox more acute, not less. The absence of evidence is not, as the saying goes, evidence of absence, but at some point, the persistent failure to find something you have good reason to expect begins to feel less like bad luck and more like an answer. Some have suggested that we are looking for the wrong thing, that an advanced civilization would not communicate via radio waves at all, that radio is a primitive technology used briefly in a species' development before being replaced by something more efficient, perhaps neutrinos, perhaps gravitational waves, perhaps something we have not yet imagined. This is plausible and also deeply frustrating, because it means the universe could be saturated with alien communication and we would be sitting in the middle of it hearing nothing, like a man in a submarine listening for birdsong. Others have suggested that the answer is simpler and bleaker. We are alone. Not alone in the sense of being the only life, but alone in the sense of being the only minds, the only species in the galaxy, or perhaps the universe, that has crossed the extraordinary sequence of improbabilities required to go from chemistry to consciousness. This is not the triumphant aloneness of a chosen species at the center of creation. It is the aloneness of a single candle in a cathedral so vast that its light reaches none of the walls, illuminating nothing but itself, burning for no audience, in a darkness that will outlast it by eons. The physicist Enrico Fermi died of stomach cancer in 1954, 4 years after asking his question, and never heard an answer. No one has. The silence continues, year after year, decade after decade, unbroken by any signal, any artifact, any evidence that the cosmos has produced a mind other than our own. And whether that silence means we are early, or we are rare, or we are doomed, or we are simply not listening with the right ears, the silence itself is undeniable. And it asks a question that is far older and far more disturbing than Fermi's. What if the universe is not merely indifferent to life, but actively hostile to it? What if the conditions required for a civilization to emerge and survive are not just rare, but unstable, perched on a knife's edge, vulnerable to disruptions that could arrive from any direction, at any time, without warning, erasing everything in an instant? The cosmos, after all, is not short of ways to kill. And some of those ways do not even require the universe to do anything unusual. Some require only that the universe continue to be exactly what it has always been, a place where the ground beneath your feet was never as solid as you thought. Imagine you are standing on what appears to be solid ground. The floor is firm beneath your shoes. The walls are steady. The ceiling holds. Everything in the room feels permanent, settled, reliable in the way that the physical world has always felt reliable, and you have no reason to question it because nothing in your experience has ever suggested that the floor might simply cease to be a floor. Now imagine being told, calmly and with mathematical precision, that the floor you are standing on is not the real floor. It is a ledge. Below it, separated from you by a barrier so thin that it should not by rights hold anything at all, lies the true floor, much lower, much more stable, and utterly incompatible with your existence. You have been standing on a shelf of frozen probability your entire life, and every atom in your body, every law of physics that permits those atoms to exist, depends on the shelf holding. If it does not hold, if the barrier is breached at any point, anywhere in the cosmos, the real floor will begin to assert itself, racing outward at the speed of light, rewriting the rules of physics as it goes, and everything built on the old rules, which is everything, will come apart, not slowly, not gently, not with warning, just gone, as if it had never been, replaced by a universe operating under new laws in which neither you nor anything like you could exist. This is false vacuum decay, and it is not a science fiction scenario. It is a prediction that sits at the intersection of quantum field theory and cosmology, taken seriously by the physicists who spend their careers working on the fundamental structure of reality, and it is, by a comfortable margin, the most total form of annihilation that physics permits. To understand it, you need to understand what physicists mean when they talk about the vacuum. In ordinary language, a vacuum is empty space, the absence of matter, the nothing between somethings. In physics, the vacuum is something else entirely. It is the lowest energy state of the fields that permeate all of space, the baseline configuration from which all particles and forces emerge. Every particle you have ever heard of, every electron, every quark, every photon, is a vibration in a quantum field, and the properties of those vibrations, the masses of particles, the strengths of forces, the rules of chemistry and nuclear physics, depend on the energy state of those fields. Change the energy state, and you change everything. The Higgs field, discovered experimentally when the Higgs boson was detected at CERN's Large Hadron Collider in 2012, is the field most relevant to this story. The Higgs field is responsible for giving mass to the elementary particles, and its value, the strength of its presence throughout the universe, determines the masses of the quarks and electrons and W and Z bosons that make up the standard model of particle physics. The value of the Higgs field is not arbitrary. It settled into its current state in the earliest moments of the universe during the period of electroweak symmetry breaking, and it has remained there ever since. The question, the one that makes physicists uncomfortable, is whether the state it settled into is truly the lowest possible energy state, the true vacuum, or merely a local minimum, a valley on a hillside that looks like the bottom of the mountain but is not. Think of it like a ball resting in a dip on a slope. The ball is stationary. It appears stable. If you gave it a small push, it would roll back to the center of the dip. But the dip is not the lowest point on the landscape. Further down the slope, past a ridge, lies a much deeper valley. The ball has settled into a false minimum, and if it ever gets over the ridge, by being given a large enough push or by finding a way through the ridge itself, it will roll down to the true minimum and never come back. Quantum mechanics provides the way through the ridge. In the classical world, a ball trapped in a dip can only escape if it is given enough energy to climb over the barrier. In the quantum world, particles and fields do not obey this restriction. They can tunnel through barriers, appearing on the other side without ever having had enough energy to climb over. The probability of tunneling is vanishingly small for everyday objects, so small that you could wait longer than the age of the universe and never see a tennis ball tunnel through a wall. But for quantum fields, over cosmological timescales and across cosmological volumes of space, vanishingly small is not the same as zero. Given enough time and enough space, even the most improbable quantum event will eventually occur. And if the Higgs field is sitting in a false vacuum, then at some point, somewhere in the universe, a quantum tunneling event could cause a tiny region of space to drop to the true vacuum state. What happens next was worked out in a landmark 1980 paper by Sidney Coleman and Frank DeLucia, and the picture they painted is not a gentle one. The region of true vacuum, once it appears, would expand. The boundary between the true vacuum and the false vacuum, the wall of the bubble, would accelerate outward, driven by the energy difference between the two states. and it would quickly approach the speed of light. Inside the bubble, the laws of physics would be different. The masses of particles would change. The strengths of forces would shift. The fine-tuned balance that allows atoms to form, that allows chemistry to happen, that allows stars to burn and planets to cool and molecules to fold into the shapes that make life possible, would be replaced by a different balance, or more likely, no balance at all. The atoms inside the bubble would disintegrate, not into their component parts, because the component parts would also be altered. The protons and neutrons would lose their structure. The quarks would lose their masses. The entire framework of matter as we understand it would dissolve into something unrecognizable, governed by rules that have never operated in our universe and never will, except inside the bubble. The bubble would have no visible precursor. It would not glow. It would not emit radiation. It would not send out a shock wave ahead of itself, because nothing can travel faster than light, and the bubble wall moves at light speed. If a bubble of true vacuum nucleated in a galaxy 1 billion light-years from Earth and began expanding this morning, you would not know about it for 1 billion years. And when it arrived, there would be no moment of awareness, no flash of pain, no time to register what was happening. The boundary would pass through you at the speed of light, and in the same instant, every atom in your body would cease to function, not because the atoms were destroyed by a force, but because the definition of what an atom is had been rewritten. You would not die in any meaningful sense, because death implies a transition from living to not living, and this would not be a transition. It would be an erasure. The region of space you occupied would simply become part of the true vacuum, and nothing that had previously existed in that region, no structure, no information, no memory, would be preserved. The question of whether the universe is actually in a false vacuum state is, as of now, an open one, and the answer depends on measurements that are exquisitely difficult to make. The mass of the Higgs boson, measured at roughly 125.1 giga-electron volts, places our universe in a curious and unsettling region on the stability diagram. If the Higgs mass were slightly higher, the vacuum would be definitively stable, the true ground state, safe from tunneling. If it were slightly lower, the vacuum would be definitively unstable and would likely have decayed already. At 125.1 giga-electron volts, the universe appears to be metastable, not in the true vacuum, but in a false vacuum that is extraordinarily long-lived. The estimated lifetime of a metastable vacuum at these values is staggeringly large, far longer than the current age of the universe, perhaps 10 to the power of 100 years or more, which means that the probability of decay in any given region of space, in any given year, is negligibly small. But negligibly small applied to the entire observable universe, with its 10 to the power of 80 particles spread across 93 billion light-years, is a different proposition than negligibly small applied to a single room. The universe is large and old and patient, and probability is not a shield, it is a postponement. There is also the uncomfortable matter of catalysis. While spontaneous quantum tunneling is the most commonly discussed mechanism for vacuum decay, it is not the only one. Sufficiently extreme concentrations of energy, the kind produced in the collisions of very high-energy cosmic rays, or, theoretically, in the most violent astrophysical events, could potentially provide enough energy to knock the Higgs field over the barrier without waiting for a random quantum fluctuation. When the Large Hadron Collider was being prepared for operation in 2008, a small but vocal group of critics raised the alarm that the particle collisions at CERN could trigger vacuum decay, destroying not just the laboratory but the entire universe. Physicists responded, correctly, that the energies produced at the LHC are far below those produced routinely by cosmic rays striking the Earth's atmosphere. and that the fact that the universe has survived billions of years of cosmic ray bombardment is strong evidence that these energies are not sufficient to initiate decay. The argument is sound. The universe has been conducting this experiment on itself since long before humans arrived, at energies far exceeding anything CERN can produce, and it has not decayed yet. But the argument works by induction, not by proof, and there is no theorem in physics that guarantees the vacuum will hold forever. What makes vacuum decay particularly haunting, beyond its total and irreversible nature, is what it reveals about the fragility of the physical constants themselves. The universe you inhabit is defined by a set of numbers: the mass of the electron, the strength of the electromagnetic force, the ratio of the proton mass to the neutron mass, the cosmological constant, and the speed of light. These numbers are not derived from any deeper principle. They are not the output of an equation. They are simply the values that the fields settled into in the first moments after the beginning, and they could, in principle, have been different. If the strong nuclear force were slightly weaker, by as little as 2%, protons and neutrons could not bind together, and there would be no atomic nuclei, no elements beyond hydrogen, no chemistry, no stars, and no planets. If the strong force were slightly stronger, all the hydrogen in the universe would have been converted to helium in the first few minutes, leaving no fuel for the long-burning main-sequence stars that provide the stable energy needed for life. If the electromagnetic force was stronger, electrons would be bound too tightly to atoms for chemical reactions to occur. If it were weaker, atoms would not form at all. The list goes on, and each example carries the same implication. The universe that permits you to exist is balanced on a razor's edge of physical constants, and the razor did not have to be this sharp. The numbers did not have to fall where they fell. Nothing in known physics dictates the values of these constants. They are inputs to the equations, not outputs from them. Some physicists find this fine-tuning deeply meaningful, a clue pointing toward a deeper theory that will explain why the constants have the values they do. Others point to the anthropic principle, the observation that if the constants were not fine-tuned for the existence of observers, there would be no observers to notice. And so the fact that we observe a fine-tuned universe is not surprising but tautological. Neither explanation is satisfying. The first requires a theory that does not yet exist. The second requires that you accept being alive as an explanation for the conditions that make you alive, which is either profound or circular depending on how much coffee you have had. The point, for the purposes of this story, is simpler and darker. The universe you inhabit is not robust. It is not built on foundations that were designed to hold. It is built on values that happen to fall in the narrow range compatible with complex structure, and those values are maintained by the energy state of fields that may not be in their final configuration. The floor, in other words, may really be a ledge, and the true floor far below, in a valley whose physics you cannot survive, is always there, always waiting, separated from you by nothing more substantial than a quantum probability. You cannot detect the approach of a vacuum decay bubble. You cannot defend against it. You cannot outrun it. You cannot even know whether one was nucleated 10 minutes ago in a galaxy 10 light years away and is currently racing toward Earth at the speed of light 10 years from arrival, because the bubble outruns any signal that could warn you of its existence. The ultimate irony of vacuum decay is that it is the one cosmic catastrophe that comes with a guarantee of ignorance. If it happens, you will never know. If it is approaching, you cannot know. And if it never happens, you will spend your existence unaware of how close the ledge came to giving way. The universe has been kind enough, so far, to remain in its current state. The constants have held. The vacuum has not decayed. The ledge has not crumbled. But "so far" is a phrase that carries no weight in cosmology, because so far is 13.8 billion years, and the universe may have trillions upon trillions of years remaining, and probability, given enough time, is not a comfort, but a certainty. The only question is when, and when is a question that quantum mechanics answers with a shrug. And while the vacuum holds, while the laws of physics remain as they are, the universe has no shortage of more immediate methods for reminding life of its fragility. The cosmos is not merely strange and vast and potentially unstable. It is armed. It carries within it forces of destruction that operate on timescales short enough and distances close enough to be not merely theoretical but historical, forces that have already reshaped the surface of this planet and extinguished entire lineages of living things without ceremony or warning. Roughly 445 million years ago, the Earth was a very different world. The continents were arranged in configurations that would be unrecognizable on a modern map. The land was barren, scoured by wind and rain, populated by nothing more complex than a thin crust of moss and lichen. All the interesting biology was in the oceans, and the oceans were thriving. Trilobites, armored in calcite, scuttled across the seafloor in their hundreds of species. Brachiopods filtered nutrients from the water in colonies so dense they formed living reefs. Nautiloid cephalopods, ancestors of the modern nautilus, cruised the open water as apex predators, their shells coiled like ram's horns, their tentacles grasping at anything that moved. The seas of the late Ordovician period were, by any measure, rich and complex and full of life that had taken hundreds of millions of years to evolve. And then, over the course of less than 1 million years, roughly 85% of all marine species vanished. The Ordovician-Silurian extinction was the first of the 5 great mass extinctions in Earth's history, and for decades its cause was debated without resolution. Ice ages were proposed, sea level changes, volcanic activity, and ocean chemistry shifts. All of these played roles, and the extinction was certainly complex and multi-causal. But in 2004, a team of astrophysicists proposed an additional mechanism, one that did not originate on Earth or anywhere near it, one that came from the sky and struck without warning, and the proposal was this: a gamma-ray burst, the most powerful type of explosion in the universe, had detonated within a few thousand light-years of Earth, bathing the planet in a torrent of high-energy radiation that stripped away the ozone layer and left the surface exposed to the full fury of the sun's ultraviolet light for years or decades afterward. Gamma-ray bursts were not discovered by astronomers looking for them. They were discovered by accident, by satellites looking for something else entirely. In 1967, the United States launched the Vela satellites, a constellation of orbital detectors designed to monitor compliance with the Partial Nuclear Test Ban Treaty by detecting the gamma-ray signatures of clandestine nuclear detonations in space. The satellites worked as intended, scanning the heavens for the telltale flash of an atomic bomb. What they found instead were gamma-ray flashes coming not from Earth or its vicinity, but from deep space, from random directions, at random intervals, with energies that dwarfed anything a nuclear weapon could produce. The discovery was classified for several years before being published in 1973, and when it was, the astronomical community was baffled. Nothing in the existing catalog of cosmic phenomena could explain these bursts. They were too bright, too brief, too energetic, and too unpredictable. For the next quarter century, gamma-ray bursts were one of the deepest mysteries in astrophysics, generating more theories than data and more arguments than answers. The mystery began to crack in the late 1990s, when satellites capable of pinpointing the locations of gamma-ray bursts in the sky allowed follow-up observations with optical and radio telescopes. The bursts were coming from distant galaxies, billions of light-years away, which meant that the energy involved was not merely large but incomprehensible. A single gamma-ray burst, lasting anywhere from a fraction of a second to several minutes, can release more energy than the sun will produce in its entire 10 billion-year lifetime. more energy in a few seconds than a star produces in 10 billion years. The numbers are so extreme that they initially seemed impossible, and the resolution came with the realization that gamma-ray bursts are not isotropic. They do not radiate equally in all directions. They are beamed, focused into narrow jets of radiation that shoot out from the poles of the collapsing or colliding object, like the beam of a lighthouse rather than the glow of a lantern. If you happen to be in the path of the beam, you see a burst of staggering intensity. If you are off-axis, you see nothing, or almost nothing. The universe is full of gamma-ray bursts that humanity has never detected because their beams were pointed somewhere else. Two types of gamma-ray burst have been identified, distinguished by their duration and origin. Long-duration bursts, lasting more than 2 seconds, and sometimes as long as several minutes, are produced by the death of extremely massive stars perhaps 40 or 50 times the mass of the Sun, whose cores collapse so violently that the resulting jets punch through the outer layers of the star and scream into space at nearly the speed of light. Short-duration bursts, lasting less than 2 seconds, are produced by the merger of two neutron stars, or a neutron star, and a stellar mass black hole, the same type of event that LIGO detects through gravitational waves. In 2017, LIGO and the Fermi Gamma-Ray Space Telescope simultaneously detected both the gravitational waves and the gamma-ray burst from a neutron-star merger, roughly 130 million light-years away, confirming for the first time that these events produce both types of signal, a chirp in gravity and a scream in light. The danger to Earth from a gamma-ray burst depends entirely on proximity and aim. A burst in a distant galaxy is spectacular but harmless, its energy spread too thin by the time it reaches us to have any effect. A burst within the Milky Way, with its beam pointed in our direction, would be a different matter entirely. At a distance of a few thousand light-years, the gamma radiation would ionize the upper atmosphere, triggering a cascade of chemical reactions that would destroy the ozone layer within days. Without ozone to block ultraviolet radiation, the surface of the Earth would be bathed in levels of UV light lethal to most surface-dwelling organisms. Phytoplankton, the base of the marine food chain, would die first. Land plants would follow. The collapse would ripple upward through the food web, and the recovery, if recovery came at all, would take millions of years. The organism that caused it all, a dying star thousands of light years away, would be long gone, its remains scattered into a nebula, utterly indifferent to the havoc its death rattle had caused on a small, rocky planet it had never known existed. The hypothesis that a gamma-ray burst contributed to the Ordovician extinction remains unproven. No direct evidence, no telltale isotope, no irradiated mineral grain has been found in the geological record to confirm it. But the hypothesis is plausible, the physics is sound, and the statistical likelihood of Earth being struck by a nearby gamma-ray burst, at least once in its 4.5 billion year history, is high enough that many astrophysicists consider it probable rather than merely possible. The universe, it seems, has already pulled this trigger. We just cannot prove when. If gamma-ray bursts are the sniper rifles of the cosmos, magnetars are the grenades, less focused, less predictable, and capable of doing extraordinary damage at surprising range. A magnetar is a type of neutron star, the ultra-dense remnant of a massive star that has exhausted its fuel and collapsed. And what distinguishes it from an ordinary neutron star is its magnetic field. The magnetic field of a typical refrigerator magnet is about 5 millitesla. The magnetic field of the Earth is about 25 to 65 microtesla. The magnetic field of a magnetar is on the order of 10 billion tesla, a number so absurd that its consequences sound fabricated. At the surface of a magnetar, the magnetic field is strong enough to distort the shapes of atoms, stretching them into long, thin cylinders aligned with the field lines. At a distance of 1,000 kilometers, it would erase the magnetic strip on every credit card on Earth. At halfway across the solar system, it would disrupt the orbits of electrons in your body's molecules. A magnetar is a fist-sized city of neutrons, with a magnetic personality so intense it borders on violence. On the 27th of December, 2004, a magnetar designated SGR 1806-20, located roughly 50,000 light-years from Earth in the constellation Sagittarius, released a giant flare, so powerful that it momentarily outshone every star in the galaxy. The burst of radiation, mostly gamma rays and X-rays, lasted about 1/10 of a second at peak intensity and released more energy in that sliver of time than the Sun emits in 250,000 years. Despite being 50,000 light-years away, the flare was powerful enough to measurably ionize Earth's upper atmosphere, compress the magnetosphere, and saturate the detectors on every gamma-ray satellite in orbit. If the magnetar had been 10 light-years away instead of 50,000, the flare would have been an extinction-level event, stripping the ozone layer and sterilizing the surface of the planet. The Earth survived the 2004 event because of distance and nothing else. There was no defense. There was no warning beyond the fraction of a second it took the radiation to arrive. The magnetar fired. The radiation crossed 50,000 light-years of space, and by the time we knew it had happened, it was already over. Supernovae, the explosive deaths of massive stars, are another entry on the cosmic threat register, and unlike gamma-ray bursts, they are not beamed. A supernova radiates in all directions, a spherical blast of light and neutrinos and high-energy particles that expands outward at a significant fraction of the speed of light. At a distance of several thousand light-years, a supernova would be a spectacular light show, but no real danger. At a distance of roughly 30 light-years, it would deliver enough radiation and cosmic rays to seriously damage the ozone layer and potentially trigger a mass extinction. At a distance of 10 light-years, it would be unsurvivable for any complex life on the surface. The nearest candidate for a near-term supernova is Betelgeuse, the red supergiant that marks the shoulder of the constellation Orion. Betelgeuse is roughly 700 light-years from Earth, give or take, and it is dying. It has exhausted the hydrogen in its core and is burning through progressively heavier elements, its outer layers swelling until the star is so large that if it replaced the Sun, its surface would extend past the orbit of Jupiter. When it finally runs out of fuel, Betelgeuse will collapse and explode in a supernova that will be visible in daylight on Earth for weeks, possibly months. It will be the most spectacular, astronomical event in recorded human history. It will also be entirely harmless. At 700 light-years, Betelgeuse is far too distant to pose any threat. The radiation will arrive, diminished by the inverse square law to a gentle wash, and the night sky will be briefly brighter, and that will be the extent of it. But Betelgeuse is not the only massive star in the neighborhood. The galaxy contains thousands of stars that will eventually go supernova, and while none currently known are close enough to threaten Earth, currently known is a qualifier that deserves emphasis, because the catalog of nearby stars is not complete, and new objects are discovered regularly, and the universe does not consult our surveys before deciding what to do. Closer to home, the threats become more tangible, more historical, and more personal. The asteroid that struck the Yucatan Peninsula roughly 66 million years ago, creating the Chicxulub crater, was approximately 10 to 15 kilometers in diameter, and it ended the age of the dinosaurs with a precision that borders on surgical. The impact released energy equivalent to roughly 10 billion Hiroshima bombs, excavating a crater more than 180 kilometers across and 20 kilometers deep. The immediate effects: a fireball that incinerated everything within 1,000 kilometers, a shockwave that flattened forests across continents, tsunamis hundreds of meters high racing across the Atlantic and Pacific, were merely the prelude. The longer-term effects were what killed most of the life on Earth. The impact ejected billions of tons of rock and dust into the atmosphere, along with vast quantities of sulfur from the gypsum-rich bedrock of the Yucatan, creating a global shroud that blocked sunlight for months or years. Photosynthesis collapsed, temperatures plummeted. Acid rain fell across the planet, poisoning fresh water and acidifying the oceans. Roughly 75% of all species on Earth went extinct, including every non-avian dinosaur, every pterosaur, every mosasaur and plesiosaur, every ammonite. A lineage of animals that had dominated the planet for over 160 million years was ended by a rock traveling at roughly 20 kilometers per second that happened to hit the wrong spot at the wrong time. The Chicxulub impact was not unique. It was merely the most consequential in recent geological history. The Earth has been struck by large objects throughout its existence, and the bombardment has not ended. On the 30th of June, 1908, something entered the atmosphere above the Tunguska region of Siberia and exploded at an altitude of roughly 5 to 10 kilometers, flattening approximately 80 million trees across 2,150 square kilometers of forest. No crater was ever found, and no fragments were conclusively recovered, which suggests the object, probably a small asteroid or comet nucleus, roughly 50 to 60 meters across, disintegrated entirely in the atmosphere. The explosion was estimated at roughly 10 to 15 megatons of TNT, 1,000 times more powerful than the bomb dropped on Hiroshima. Had it arrived 4 hours later, the Earth's rotation would have placed St. Petersburg beneath the blast. On the 15th of February, 2013, a meteor roughly 20 meters in diameter entered the atmosphere above Chelyabinsk, Russia, at a speed of roughly 19 kilometers per second and exploded at an altitude of roughly 30 kilometers. The airburst released energy equivalent to roughly 500 kilotons of TNT, about 30 times the Hiroshima bomb. The shock wave blew out windows across the city, injuring roughly 1,500 people, most of them cut by flying glass. The Chelyabinsk meteor was not detected before it arrived. No telescope saw it coming. No warning was issued. The first indication that anything unusual was happening was the flash of light, brighter than the sun, that illuminated the morning sky, followed seconds later by the shock wave that shattered every window facing the blast. Dashboard cameras across the city captured the event, producing footage that went viral within hours. And the footage is remarkable not for the explosion itself, but for the reactions of the drivers, the calm, the confusion, the slow dawning realization that something extraordinary and terrifying had just happened, and that there had been absolutely nothing anyone could have done about it. NASA's Center for Near-Earth Object Studies tracks thousands of asteroids and comets whose orbits bring them close to Earth, and the catalog grows annually as survey telescopes identify new objects. The DART mission, launched in 2021, successfully altered the orbit of the small asteroid moonlet Dimorphos by crashing a spacecraft into it at roughly 6 kilometers per second, demonstrating for the first time that humanity possesses, at least in principle, the ability to deflect an incoming asteroid. The test was a success. It was also a proof of concept that requires years or decades of advance warning to be useful, because deflecting an asteroid is a matter of applying a tiny force over a long period, nudging it gradually off course, and a tiny force applied at the last minute accomplishes nothing. If a Chicxulub-sized asteroid were discovered on a collision course with Earth, and the warning time were less than a few years, the current state of human technology would offer no defense. The species that split the atom and walked on the moon would watch the rock approach and be unable to stop it. And then there is the sun itself, the star that sustains all life on Earth and is also, in its own quiet way, capable of ending civilization without exploding, without dying, without doing anything more dramatic than having a bad day. The sun's surface is a roiling sea of plasma, threaded with magnetic field lines that twist and snap and reconnect in patterns of staggering complexity. When these magnetic field lines become sufficiently tangled and suddenly release their stored energy, the result is a solar flare, a burst of electromagnetic radiation that crosses the distance from the Sun to the Earth in roughly 8 minutes. Flares are common and usually harmless, but occasionally, a flare is accompanied by a coronal mass ejection, a vast cloud of magnetized plasma hurled outward from the Sun's surface at speeds of up to 3,000 kilometers per second, carrying with it a magnetic field strong enough to interact violently with the Earth's own magnetosphere. On the 1st of September, 1859, a British astronomer named Richard Carrington was sketching sunspots at his private observatory when he witnessed something no one had ever seen before. A brilliant white flare erupting from the surface of the Sun, so bright it was visible in white light, a rarity that indicated enormous energy. 17 hours later, the coronal mass ejection associated with that flare struck Earth's magnetic field, and the result was the most powerful geomagnetic storm in recorded history. The Carrington event, as it came to be known, produced auroras so vivid they were visible in the Caribbean and Colombia. Telegraph systems across North America and Europe failed spectacularly, with operators receiving shocks and equipment catching fire. Some telegraph lines continued to transmit messages even after being disconnected from their batteries, powered by the electrical currents induced in the wires by the storm itself. In 1859, the most complex electrical infrastructure on the planet was the telegraph network, and the Carrington event damaged it severely but not catastrophically. A Carrington-class event today would be a different story entirely. Modern civilization depends on an electrical grid of extraordinary complexity and extraordinary fragility, a network of transformers and transmission lines and substations designed to operate within narrow parameters and deeply vulnerable to the induced currents that a major geomagnetic storm would produce. A 2013 study by Lloyd's of London estimated that a Carrington-class event striking today could cause between $0.6 and $2.6 trillion in damage in the United States alone, with recovery times for the most severely affected transformers ranging from 4 to 10 years. 4 to 10 years without power, in a civilization that cannot feed itself without refrigeration, cannot pump water without electricity, cannot communicate without networks that require electricity to function. The 2012 event that missed Earth by roughly 9 days, a coronal mass ejection of Carrington-class magnitude that passed through Earth's orbital path just after the planet had moved out of the way, was estimated by NASA to have been the most powerful solar storm in at least 150 years, 9 days. The margin between an ordinary Tuesday and the collapse of electrical infrastructure across an entire hemisphere was 9 days and the rotation of the Earth. The common thread running through all of these threats is the same. The universe does not need exotic physics to be dangerous. It does not need vacuum decay or theoretical instabilities or hypothetical dark forces. It needs only the ordinary machinery of stellar evolution, gravitational dynamics, and electromagnetic interaction, the same processes that built the solar system and made the Earth habitable in the first place. The forces that created you are the same forces that can destroy you, and they have done so before. To species far more numerous and far more successful than yours, and they were not punished for it, and they did not learn from it because they are not capable of punishment or learning. They are processes, blind and mechanical, operating on timescales that make human history look like a single frame in a film that has been running for billions of years. And the film is still running. The projector has not stopped. But the film has an ending, and the ending is not an explosion or a collision or a burst of radiation from a dying star. The ending is quieter than that. The ending is the slow, patient, irreversible winding down of everything, the gradual dimming of every light, the cooling of every fire, the stilling of every motion, until there is nothing left but cold and darkness, and a silence so complete that the word silence does not begin to describe it. Every fire you have ever watched die tells the same story. The flames rise, bright and eager, consuming their fuel with a hunger that seems inexhaustible. Then they slow. The wood becomes embers. The ember becomes ash. The heat radiates outward, thinning and cooling, spreading into the walls and the air and the night, until it is indistinguishable from the temperature of everything else. The fire does not end with a bang. It ends with a settling, a leveling, a quiet diffusion of energy from where it was concentrated to where it was not, until the difference between hot and cold has been erased, and there is nothing left to drive the process further. You have watched this happen 100 times. You have never once seen it run in reverse. You have never seen scattered heat gather itself from the walls of a room and concentrate into a flame. You have never seen ash reassemble into wood. You have never seen a broken egg climb off the floor and seal itself back into its shell. And you never will, because the story that fire tells is the story of the universe, and the universe only tells it in one direction. The reason is entropy, and entropy is the closest thing physics has to a prophecy of doom. In the language of thermodynamics, entropy is a measure of disorder, of the number of possible microscopic arrangements a system can have while still looking the same from the outside. A neatly stacked deck of cards has low entropy. The arrangement is specific, ordered, one particular configuration out of the vast number of possible shuffles. A randomly shuffled deck has high entropy. It could be any of billions of arrangements, and no particular order has been imposed. The second law of thermodynamics states that in any closed system, entropy never decreases. It can stay the same, it can increase, it cannot go backwards. Energy flows from hot to cold, from concentrated to dispersed, from ordered to disordered, and this flow is not a tendency or a habit or a preference. It is a law, as fundamental as gravity, and unlike gravity, it has a direction. It points the same way every time. It points toward equilibrium. It points toward the ash. This is the arrow of time. Not a physical arrow, not a force, not something that pushes events from past to future, but a statistical inevitability so overwhelming that it might as well be a commandment. The reason time feels like it moves in one direction. The reason you remember yesterday but not tomorrow. The reason causes precede effects and eggs do not unbreak is that the universe began in a state of extraordinarily low entropy and has been increasing ever since. Every process that has ever occurred, from the fusion of hydrogen in the cores of stars to the firing of neurons in your brain to the slow rusting of an abandoned car, is entropy increasing, energy dispersing, order yielding to disorder, one step at a time, irreversibly, toward a final state of maximum disorder from which no further change is possible. That final state has a name. Physicists call it heat death, and the name is misleading because it is not hot. It is the opposite of hot. It is a state in which all energy has been evenly distributed across all of space, in which no temperature differences exist, no gradients remain, no pockets of concentrated energy survive from which work could be extracted or structure could be built. It is not the death of heat. It is the death of difference. It is the universe at thermal equilibrium. Every point the same temperature as every other point. Every region indistinguishable from every other region. A cosmos-wide bath of radiation so cold and so diffuse that nothing can happen, because happening requires a difference between here and there, between now and then, between hot and cold, and all such differences will have been erased. But heat death is not an event. It is not a moment that arrives with a sound or a flash or a sensation. It is a process, unimaginably slow, stretching across timescales that make the current age of the universe look like the first syllable of a sentence that will take longer to speak than the human mind can conceive. The universe is 13.8 billion years old. What lies ahead is so much longer that the comparison is almost meaningless, like comparing the width of a single atom to the diameter of the observable cosmos. And the journey from here to heat death passes through stages, each one stranger and more desolate than the last, each one lasting immensely longer than the one before, each one stripping away another layer of the cosmos until nothing remains. The current era, the one in which you live, is called the stelliferous era, the age of stars. It began a few 100 million years after the universe's birth, when the first hydrogen clouds collapsed under their own gravity and ignited nuclear fusion, and it will continue for trillions of years, fueled by the slow, patient burning of the smallest and most efficient stars. The Sun, a medium-sized star, with a lifespan of roughly 10 billion years, is already halfway through its fuel supply. In approximately 5 billion years, it will exhaust the hydrogen in its core, swell into a red giant, large enough to engulf Mercury, Venus, and possibly Earth, and then shed its outer layers into space, leaving behind a white dwarf the size of the Earth and the mass of a star. A cooling ember that will glow for billions of years before fading to black. But the Sun is not the last star. The smallest red dwarf stars, barely massive enough to sustain fusion, burn their fuel so slowly and so completely that they can shine for trillions of years. A red dwarf, a tenth the mass of the Sun, dim and cool and crimson, barely visible even from nearby, will still be burning long after every sun-like star in the universe has exhausted itself and gone dark. The last red dwarfs will flicker on for perhaps 100 trillion years, roughly 10,000 times the current age of the universe, and they will be the last natural sources of light the cosmos will ever produce. When they finally exhaust their hydrogen, when the last nuclear reaction in the last red dwarf sputters to a halt, the stelliferous era will end, and the universe will enter a darkness from which it will never emerge. What follows is the degenerate era, a name chosen not for moral judgment, but for a term in quantum physics. In this epoch, which stretches from roughly 10 to the power of 15 to 10 to the power of 39 years after the beginning, the only stellar remnants left will be white dwarfs, neutron stars, and the already discussed gravitational abysses that populate galactic centers and scatter the spaces between. White dwarfs will cool, slowly, their residual heat radiating into space over trillions of years, their surfaces dimming from white to yellow to red to a deep, invisible infrared, and finally to black. These black dwarfs, as they will be called, will be composed of carbon and oxygen, crystallized into a lattice structure, essentially diamond spheres the size of planets, floating in the dark, emitting nothing, reflecting nothing, orbiting nothing, or orbiting each other in slow, silent dances that no eye will ever see. If protons are stable, this is where the story effectively ends for ordinary matter. The black dwarfs and neutron stars will persist forever, cold and inert, monuments to a universe that once burned. But protons may not be stable. Several grand unified theories, which attempt to merge 3 of the 4 fundamental forces into a single framework, predict that protons have a finite lifetime, perhaps 10 to the power of 36 years, perhaps 10 to the power of 41 years, perhaps longer. No proton decay has ever been observed, despite experiments designed specifically to detect it, including the Super Kamiokande detector in Japan, a vast tank of 50,000 tons of ultra-pure water buried beneath a mountain, lined with 11,000 photomultiplier tubes waiting to catch the faint flash of light produced by a decaying proton. The detector has been running for decades. Not a single proton has been caught in the act. but the predicted lifetime is so enormously long that the failure to observe decay so far is entirely consistent with the theory. The experiment would need to run for a duration many orders of magnitude, longer than the current age of the universe, to provide a definitive test. If protons do decay, the consequences for the far future are absolute. Over the course of 10 to the power of 36 to 10 to the power of 41 years, every proton and every neutron and every atom and every black dwarf and neutron star in the universe will disintegrate, converting their mass into electrons, positrons, neutrinos, and photons. The solid remnants of the stellar era will evaporate, not through any dramatic process, but through the slow statistical accumulation of individual particle decays, one proton at a time, over timescales so long that the degenerate era itself, lasting quadrillions of years, is a momentary flash by comparison. By the time proton decay is complete, there will be no atoms left in the universe, no molecules, no crystals, no solid matter of any kind. Only a thin, cooling gas of leptons and photons, drifting through a space that has expanded beyond comprehension. And then the black hole era begins. With all ordinary matter dissolved, the only macroscopic objects remaining will be the gravitational abysses themselves, those regions of spacetime where matter once fell and could not return, still carrying the mass of millions or billions of suns, still warping space around them, still possessing their event horizons, their spins, their silhouettes against a background of nothing. They will be the last structures in the universe, and they will endure for an almost inconceivable length of time, because the evaporation process that slowly converts their mass into radiation, the mechanism that Stephen Hawking described in 1974, operates on timescales that dwarf everything discussed so far. A stellar mass remnant would take roughly 10 to the power of 67 years to evaporate. The supermassive monsters at the centers of former galaxies would take 10 to the power of 100 years, a number called a googol, a 1 followed by 100 zeros, a duration so vast that no human analogy can touch it. But even a googol years is finite, and finite means it ends. The last and largest gravitational abyss in the universe will shrink, particle by particle, photon by photon, its event horizon contracting as its mass bleeds away into the void. As it shrinks, it will grow hotter, its radiation becoming more energetic, its evaporation accelerating, the process that began as a glacial trickle becoming, in its final moments, a torrent. And then, in one last burst of light and energy, it will vanish. The event horizon will close. The singularity, if it still existed in any meaningful sense, will be gone. The last structured object in the universe will have dissolved into a spray of particles and radiation that will disperse into the void and never reconcentrate. That final flash will be the last light the universe ever produces. After it fades, there will be nothing left but a thin, uniform gas of photons, electrons, positrons, and neutrinos, all at a temperature asymptotically approaching absolute zero, all drifting through a space that continues to expand, carrying them further and further apart, thinning the gas, cooling the radiation, reducing the density of the cosmos toward, but never quite reaching, zero. This is the dark era, and it will last forever. Not for a long time, not for an almost infinite time, forever. The dark era has no end, because nothing can happen in it. No energy gradients exist to drive any process. No structures can form, because the density is too low and the temperature too cold and the expansion too relentless. The universe will be, for all practical and impractical purposes, dead, and it will remain dead for eternity, unless. The Big Rip is an alternative ending, and in some ways it is more dramatic, though not necessarily more terrifying, than heat death. If the force driving the accelerating expansion of the universe is not constant but increasing over time, a variant called phantom energy, then the expansion rate will not merely accelerate but grow without limit. Space will stretch faster and faster, and the force pulling things apart will eventually overwhelm every other force in the universe. First, galaxy clusters will be torn apart, their constituent galaxies receding from each other beyond the point of gravitational return. Then individual galaxies will be disrupted, their stars scattered. Then solar systems will be dismembered, planets flung from their orbits. Then stars and planets themselves will be torn apart, their material pulled into expanding clouds of debris. Then atoms will be ripped open, their electrons stripped from their nuclei. Then atomic nuclei will disintegrate, their protons and neutrons pulled apart. And finally, in the last fraction of the last second, space-time itself will be torn apart, the fabric of reality shredded by its own expansion, and the universe will end not in silence, but in a single, infinite, everywhere, at once, act of destruction. Calculations suggest the Big Rip, if phantom energy is real, could occur as soon as 22 billion years from now, which is less than twice the current age of the universe. Current observations are consistent with dark energy being constant rather than increasing, which means the Big Rip is unlikely but not ruled out. The error bars on the equation of state of dark energy are still wide enough to admit the possibility of cosmic dismemberment. The Big Crunch, once considered the most likely fate of the universe, has largely fallen out of favor since the discovery of accelerating expansion, but it deserves mention as the mirror image of the Big Rip. In a Big Crunch scenario, the expansion of the universe eventually reverses, either because gravity wins out or because the nature of dark energy changes and the cosmos begins to contract. Galaxies draw closer together. Space shrinks. The temperature rises. The cosmic microwave background, long since cooled to near absolute zero, begins to heat up again, growing brighter and hotter as space compresses. In the final moments, the universe collapses back into the ultra-dense, ultra-hot state from which it emerged, a singularity, a point of infinite density, a mirror of the beginning. Whether anything emerges from the other side, whether the universe bounces and begins again, is a question that physics cannot currently answer. Some cyclic models propose exactly this: an infinite sequence of big bangs and big crunches, universes blooming and wilting like flowers in an eternal garden. The models are speculative, and the evidence at present does not support them. The expansion is accelerating, not slowing, and the cosmos appears to be heading not toward a fiery collapse, but toward a cold, dark, empty eternity. And in that eternity, one final possibility remains, and it is perhaps the strangest and most disturbing idea in all of physics. In a universe governed by quantum mechanics, nothing is truly impossible. Improbable? Yes. Staggeringly, mind-breakingly, universe-destroyingly improbable? Yes. But not impossible. Given infinite time and a non-zero probability, every possible configuration of matter and energy will eventually occur simply through random quantum fluctuations. A single particle might pop into existence from the vacuum. A pair of particles might appear. A molecule. A complex structure. And if you wait long enough, an unimaginably long time, a duration so vast that writing the number of years would require more digits than there are atoms in the observable universe, a random quantum fluctuation could, in principle, produce a fully formed brain, complete with memories and thoughts and a momentary flicker of consciousness, floating alone in the void, experiencing a single instant of awareness before dissolving back into nothing. This hypothetical entity is called a Boltzmann brain, named after the 19th century physicist Ludwig Boltzmann, who first grappled with the statistical foundations of entropy and thermodynamics. The concept was originally raised as a thought experiment, a reductio ad absurdum designed to test the logical consistency of certain cosmological models. But it has taken on a life of its own, because in a universe that faces an infinite dark era, the probability of Boltzmann brains eventually forming is not zero, and over infinite time, anything with non-zero probability becomes certain. The implication is disquieting. In the far, far, far future of the cosmos, long after every star is burned out and every atom is decayed and every gravitational remnant has evaporated, the only observers that will ever exist will be random assemblages of matter, briefly conscious, immediately dying, their experiences entirely disconnected from any history or context or meaning. Some cosmologists have taken the Boltzmann brain problem seriously enough to use it as a constraint on theoretical models. If a cosmological model predicts that Boltzmann brains will vastly outnumber ordinary observers like you and me, then the model has a problem, because it would mean that your own consciousness is almost certainly a random fluctuation rather than a product of billions of years of evolution on a planet orbiting a star, and your memories, your experiences, your entire sense of a coherent past are statistically likely to be false, generated spontaneously along with the brain that contains them. This is a conclusion that most physicists regard as absurd, which means that either the dark era is not truly infinite, or the quantum vacuum does not behave the way current theory predicts over such timescales, or something else is happening that prevents the universe from spending eternity generating random hallucinating brains in the void. None of these alternatives is fully understood. The Boltzmann brain problem remains open, a philosophical wound at the boundary of physics and metaphysics, bleeding quietly into the dark. So, this is the future of the cosmos. Not one ending, but several possible endings, each more desolate than the last, and all of them pointing in the same direction, away from complexity, away from structure, away from light, away from warmth, away from life, and toward a state of maximum entropy from which no return is possible. The universe began in a flash of unimaginable energy and will end in a whisper of unimaginable cold. Everything between, everything you have ever known or will ever know, the entire catalog of human experience, the entire history of life on Earth, the entire blazing spectacle of the stelliferous era, with its trillions of galaxies and its quadrillions of stars, is a brief, shining, improbable interlude between the fire and the ice, a flicker, a spark, a candle lit in a cathedral of infinite darkness, burning for an instant that the universe will not remember. You are made of matter that was forged in the furnaces of dying stars, assembled by gravity, animated by chemistry, and given consciousness by a process that no one fully understands. You exist in the sliver of cosmic time, when the universe is complex enough to produce minds and young enough to still have light. You will not exist for long, neither will your species. Neither will your planet, your star, your galaxy, or any galaxy. But you exist now, in this moment, in this unlikely, temporary, magnificent arrangement of atoms that knows it is an arrangement of atoms and can contemplate the darkness that preceded it and the darkness that will follow. And that, in a universe that owes you nothing and promised you less, is not nothing. The cosmos is under no obligation to make sense to you. It is under no obligation to comfort you, to provide meaning, to justify your existence, or to care that you are here. It is vast and old and cold, and will outlast everything you love by a margin that makes mockery of the word margin. But it made you, somehow, through some chain of events so improbable that no honest accounting of the odds would ever predict it. The universe produced a creature capable of looking back at it and asking why. That creature is you, and you are awake, for now, in a cosmos that is mostly asleep, listening to a story about how it all ends, and the fact that you can hear it, the fact that you care about the answer, the fact that the question matters to you at all, is the most defiant and extraordinary thing that matter has ever done.